There are places where history falls silent. No written records explain them. No surviving blueprint reveals how they were built. Only enormous stones, impossible architecture, and unanswered questions remain. For centuries, archaeologists have measured, excavated, and reconstructed these ancient sites, uncovering remarkable evidence of human ingenuity. Yet the deeper the investigation goes, the more difficult they become to explain. Structures that should not have been possible continue to stand, while the knowledge that created them seems to have vanished without a trace. These are not simply ruins from a forgotten age. They are enduring reminders that the story of human civilization may still be missing some of its most extraordinary chapters. Bolshoi Zayatsky Island, part of Russia's Solovetsky archipelago in the White Sea, preserves one of Europe's most enigmatic prehistoric landscapes. Rather than monumental temples, fortifications, or ancient settlements, the island is known for an extraordinary concentration of stone labyrinths constructed directly across its exposed coastal bedrock. Russian scholars first documented these structures during the 19th century, and systematic archaeological research beginning in the early 20th century revealed a site unlike any other in northern Europe. 13 stone labyrinths survive on Bolshoi Zayatsky alone, while more than 30 have been identified across the Solovetsky Islands. Most researchers date their construction to between roughly 1000 BCE and the beginning of the Common Era, although the exact age of individual labyrinths remains uncertain, because almost no organic material suitable for radiocarbon dating has survived. More than a century of archaeological investigation has clarified when these remarkable geometric monuments were probably built, yet their builders, their purpose, and the mathematical knowledge behind their design remain unresolved. At first glance, the labyrinths appear deceptively simple. They are formed from thousands of fist-sized granite boulders, carefully arranged into continuous winding paths between approximately 6 and 25 meters in diameter. Looking from ground level, they resemble little more than irregular rings of stones. Only after aerial photography, drone surveys, and detailed topographic mapping became available did researchers fully appreciate their remarkable geometric organization. Nearly every labyrinth follows a double spiral design, leading toward a central stone cairn before returning along the same continuous path. There are no intersections, no dead ends, and no alternate routes. Unlike later hedge labyrinths or maze puzzles, these monuments were never intended to confuse visitors. Instead, every movement through them appears to have been predetermined by an invisible geometric plan established long before the first stone was placed. That realization immediately raises one of the site's greatest mysteries. Constructing smooth concentric curves using thousands of irregular stones across uneven glacial bedrock requires careful planning and consistent measurements. The distance separating adjacent pathways remains surprisingly uniform despite variations in terrain, while the curvature maintains an impressive level of symmetry from one side of each labyrinth to the other. Achieving that degree of regularity without written plans, surveying instruments, or standardized measuring devices suggests that the builders possessed a sophisticated practical understanding of geometry. Archaeologists can identify the finished patterns with great precision today using satellite imagery and digital mapping. Yet they still cannot explain how prehistoric builders established those layouts accurately from ground level, where the complete design would have been almost impossible to visualize. The question becomes even more intriguing because the labyrinths appear to prioritize geometric perfection over practical necessity. A simple ceremonial pathway could have been created with far fewer stones and considerably less effort. Instead, the builders repeatedly invested enormous labor in maintaining balanced spirals whose mathematical appearance becomes obvious only when viewed from above. Nothing indicates that prehistoric communities possessed elevated observation platforms capable of revealing the finished design. The paradox therefore remains unresolved. The most striking characteristic of these monuments is largely invisible to the people constructing them, yet they consistently achieved it across multiple independent structures. As excavation expanded across Bolshoi Zayatsky, archaeologists discovered that the mystery extends beyond individual labyrinths. Their placement across the island follows patterns that appear intentional rather than random. Most occupy elevated coastal terraces overlooking the White Sea, often separated by relatively consistent distances while avoiding marshes and unstable ground. Several share nearly identical dimensions, and many repeat the same geometric template with only minor modifications. Instead of isolated monuments built independently over centuries, the collection resembles a carefully organized landscape whose overall spatial arrangement may have carried symbolic meaning. No surviving evidence explains why specific locations were selected, yet statistical studies suggest that the distribution is unlikely to be accidental. The orientation of the labyrinths has generated decades of debate. Some researchers argue that certain entrances align approximately with true north, while others correspond broadly with the positions of sunrise or sunset during seasonal events such as the summer solstice. These proposals have encouraged theories that the labyrinths functioned partly as astronomical monuments. However, every astronomical interpretation encounters the same obstacle. While some structures fit these alignments reasonably well, others deviate significantly. If celestial observation governed the entire complex, consistency would be expected across all examples. If the alignments are merely coincidental, then the repeated appearance of similar orientations becomes difficult to dismiss completely. Despite increasingly accurate GPS measurements and digital landscape reconstruction, no single astronomical model successfully explains every labyrinth on the island. Dating the site presents another major challenge because the labyrinths contain remarkably little archaeological material. Excavations have recovered scattered stone tools, fragments of pottery, hearth remains, and small quantities of charcoal from nearby contexts, but direct associations with individual labyrinths remain limited. No inscriptions identify their builders. No written traditions describe their construction. There are no monumental burials, permanent settlements, or ceremonial buildings capable of revealing who organized such a remarkable project. Chronology, therefore, depends largely on environmental evidence, shoreline displacement studies, and comparison with similar northern European sites. These methods provide broad estimates but cannot identify the specific community responsible for creating the labyrinths. Their remote setting deepens the mystery. Bolshoi Zayatsky lies within a harsh maritime environment where winters are long and severe. Building even a single labyrinth required collecting, transporting, and positioning thousands of stones with remarkable consistency across exposed rocky ground. Constructing more than a dozen on the same island demanded a level of organization difficult to reconcile with a temporary seasonal camp. The labor invested seems disproportionate if the monuments served only a simple practical purpose. Archaeologists continue asking why prehistoric communities repeatedly return to such an isolated island to construct geometrically sophisticated monuments whose function remains uncertain. Several theories attempt to explain that extraordinary investment, yet none accounts for every observation. Ethnographic comparisons suggest the labyrinths may have played roles in initiation ceremonies, seasonal rituals, symbolic journeys between life and death, or spiritual beliefs connected with the surrounding sea. Fishermen in later centuries even developed folklore claiming that walking the labyrinth trapped evil spirits, although these traditions appeared long after the monuments were built and cannot be treated as evidence for their original purpose. Other researchers proposed that the spirals represented cosmological concepts rather than physical pathways, making the geometry itself the essential feature. If that interpretation is correct, then every carefully measured curve formed part of a symbolic language now completely lost. The mystery expands beyond Russia, because remarkably similar stone labyrinths occur along the coasts of Finland, Sweden, Norway, and Estonia. Many display nearly identical double spiral layouts, despite being separated by hundreds of kilometers. Yet archaeology has never demonstrated the existence of a single cultural tradition linking every example. Either knowledge of this distinctive geometric design spread widely across Northern Europe over many generations, or separate communities independently developed almost identical solutions to the same symbolic problem. Neither possibility has been conclusively demonstrated, leaving the shared geometry as another unanswered question. Menajra Temples, Malta. More than 5,600 years ago, on a limestone cliff overlooking the Mediterranean Sea, builders created a monument whose geometry still aligns with the rising sun so precisely that modern archaeologists continue to debate how such accuracy was achieved long before mathematics, engineering, or astronomy were ever recorded on the island. The temples stand on the southern coast of Malta and remained buried beneath accumulated soil and collapsed stone for centuries, before being documented by British naval officers during the 19th century. Serious archaeological excavations began in the early 20th century, eventually revealing that Menajra formed part of one of the world's oldest surviving monumental temple complexes. Radiocarbon dating places its principal construction between approximately 3,600 and 3,200 BCE, making it significantly older than Stonehenge in its final form, and older than the Great Pyramid of Giza by roughly 1,000 years. Excavations uncovered carefully shaped limestone blocks, altars, decorated stone panels, animal remains, pottery, and evidence of repeated ceremonial activity, yet they produced almost nothing capable of explaining how the builders planned a structure whose geometry still performs with remarkable precision today. What immediately separates Menajra from many other prehistoric monuments is that its builders were not simply arranging stones into an impressive enclosure. They created a carefully oriented architectural instrument that interacts with sunlight throughout the year. The lower temple faces the southeastern horizon, and on the mornings of both the spring and autumn equinoxes, the first rays of the rising sun pass directly through the central entrance before illuminating the inner axis of the sanctuary. During the summer solstice, sunlight reaches one side of the interior, while during the winter solstice, it strikes the opposite side. These observations have been repeatedly confirmed through modern surveys and direct monitoring, demonstrating that the alignments are genuine astronomical phenomena rather than later speculation. Such accuracy immediately raises a question that has never been fully answered. More than 5,600 years ago, how did a society without written mathematics, precision instruments, optical devices, or metal surveying equipment determine the exact positions where the sun would rise throughout an entire solar year? The challenge becomes even greater when considering the movement of the sun itself. The rising point on the horizon shifts continuously from one day to the next, reaching its northernmost position at the summer solstice before gradually reversing toward its southernmost position during winter. Accurately predicting this cycle requires years of careful observation, because a single year's measurements can easily be distorted by weather or atmospheric conditions near the horizon. Modern researchers can reproduce these alignments using astronomical software, yet reconstructing the knowledge that originally produced them remains impossible because no measuring tools, diagrams, or written instructions have ever been discovered at the site. The geometry still functions perfectly, but the intellectual process behind it disappeared thousands of years ago. As archaeologists examined the architecture more closely, they found that the astronomical alignment was only one layer of a far more sophisticated design. The temple's plan follows an exceptionally balanced arrangement of curved apses positioned around a central axis, creating a layout that appears almost symmetrical despite the irregular terrain on which it was built. The walls maintain consistent curvature, the passageways remain remarkably uniform in width, and the entrance directs both movement and sunlight toward carefully selected focal points. None of these relationships seem accidental. Instead, they suggest that the builders followed a predefined geometric concept before construction even began. Yet no evidence survives to reveal whether this geometry existed only in memory, whether it relied upon ropes and wooden stakes, or whether it represented a measurement system that vanished long before recorded history. The enormous limestone blocks introduce another unanswered problem. Some individual megaliths weigh more than 20 tons, while several approach 50 tons. Unlike many later civilizations that possessed bronze tools, wheeled transport, or documented lifting systems, the people who built Menasdra lived during Malta's Neolithic period. They worked primarily with stone tools and materials available on the island itself. Even if prehistoric communities could transport these blocks using rollers, sledges, or earthen ramps, those methods alone cannot explain why the finished walls fit together with such consistency. Many contact surfaces were carefully dressed. Corners remain surprisingly regular, and the monument has survived thousands of years despite exposure to sea winds, seasonal temperature changes, and continuous erosion from salt carried inland by Mediterranean storms. Equally remarkable is the relationship between the architecture and the surrounding landscape. The temples were not constructed on a perfectly level platform but on naturally uneven limestone overlooking the sea. Maintaining an accurate astronomical orientation under such conditions required controlling both elevation and horizontal direction simultaneously. Any significant deviation during construction would have altered the path of sunlight inside the building, especially during the solstices when the sun rises at its most extreme positions. Modern surveying instruments can calculate these angles within seconds, but the prehistoric builders had only repeated observation of nature. Whether they established reference lines using distant landmarks, temporary wooden markers, or methods now completely forgotten, remains unknown. Another mystery emerges when considering the long-term stability of the alignments themselves. Over thousands of years, structures experience gradual movement caused by erosion, earthquakes, and natural settlement of the ground. Malta has not remained geologically unchanged since the Neolithic period, yet the solar phenomena at Menasdra continue to occur with impressive accuracy. Some researchers argue that the monument originally possessed even greater precision before minor shifts accumulated over millennia, while others believe the builders intentionally designed broad enough alignments to accommodate natural variation. Neither explanation has been proven because the original construction methods were never recorded. Scattered throughout the complex are carefully carved openings and smaller apertures whose functions remain uncertain. Some clearly admit sunlight at particular moments, reinforcing the interpretation of Menasdra as a solar sanctuary. Others, however, do not correspond neatly with known solar events. Their orientations have inspired suggestions ranging from ritual symbolism to observations of specific stars or lunar cycles, yet no consensus exists. Unlike later civilizations that left inscriptions explaining ceremonial architecture, the builders of Menasdra left only stone. Every hypothesis must therefore rely upon geometry itself, rather than written testimony. Perhaps the most remarkable aspect of Menasdra is that it developed in relative isolation. During the 4th millennium BCE, Malta possessed no documented writing system, no monumental mathematical texts, and no surviving evidence of contact capable of transferring advanced architectural knowledge from Egypt or Mesopotamia. whose great stone monuments had not yet reached their most famous forms. Even so, the island's builders demonstrated an understanding of orientation, symmetry, proportion, and long-term solar observation that rivals many much later ceremonial landscapes. Archaeologists can measure every wall, model every alignment, and simulate every sunrise with extraordinary precision. Yet none of those achievements explains how the original designers transformed repeated observations of the sky into enduring geometry carved into stone. On the volcanic summit of Tatichev Kamen in northeastern North Macedonia lies Kokino, a Bronze Age sanctuary where a series of narrow rock notches align with the rising sun on specific days of the year. Viewed from a single stone seat, the precision of these alignments has led some researchers to identify Kokino as one of Europe's oldest astronomical observatories, while others argue that the geometry is nothing more than an extraordinary coincidence created by nature. Nearly 4,000 years after the site was first used, that debate remains unresolved. The site first attracted archaeological attention in 2001, when excavations directed by archaeologist Jovika Stankovsky uncovered Bronze Age ceramics, stone tools, molds used for bronze casting, and evidence that people had occupied the summit roughly 3,800 years ago. Soon afterward, physicist and astronomer Gyuri Chenev began studying the surrounding rock formations and proposed that several carefully modified notches on the eastern horizon corresponded to the sunrise during the summer solstice, winter solstice, and both equinoxes. The interpretation transformed Kokino from an isolated mountain settlement into one of the most debated prehistoric astronomical sites in Europe. Yet the evidence immediately raised questions that remain unresolved today. Unlike monumental observatories built from transported stone blocks, Kokino takes advantage of an extinct volcanic peak, rising approximately 1,013 meters above sea level. Millions of years of erosion fractured the andesite bedrock into natural platforms, vertical walls, and narrow openings overlooking the eastern horizon. The remarkable feature is that prehistoric builders did not simply occupy the landscape, but appear to have reshaped selected parts of it with extraordinary restraint, carving seats, terraces, and observation points while preserving the mountain's original geometry. Because the modifications are relatively subtle, researchers continue to debate where nature ends and human engineering begins, making every alignment difficult to interpret with absolute certainty. That uncertainty becomes even more intriguing when examining the geometry of the observation system itself. The proposed astronomical markers are not scattered randomly across the summit. Instead, they form a sequence of narrow sightlines that only function correctly when viewed from extremely specific positions. Standing a few meters away is often enough for the alignment to disappear entirely. From the principal stone seat, however, the sun appears to emerge directly through carefully positioned gaps in the rock on significant dates of the solar year. Such a configuration suggests that the builders were not merely watching the sunrise, but deliberately controlling the observer's position, transforming the surrounding landscape into a fixed geometric instrument. Achieving that level of precision would have required far more than casual observation. The position of sunrise changes continuously along the horizon throughout the year, reaching its northernmost point during the summer solstice, before gradually reversing toward the winter solstice. Detecting that annual cycle demands repeated observations over many years, while identifying the exact turning points requires careful comparison between successive seasons. Any error in selecting the observation point or carving a marker would shift the apparent alignment enough to invalidate the entire system. Yet several proposed markers continue to correspond closely with modern astronomical calculations, despite nearly 4 millennia of environmental change, suggesting that the builders possessed a sophisticated practical understanding of long-term celestial motion. The geometry becomes even more remarkable because the horizon itself is highly irregular. Unlike an ideal mathematical plane, the eastern skyline surrounding Kokino consists of distant mountains with constantly changing elevations. Ancient observers, therefore, could not simply divide angles using abstract geometry. Instead, they had to account for the true profile of the surrounding landscape, calculating where the sun would first become visible above each ridge, rather than where it existed geometrically below the horizon. Modern archaeoastronomers use digital elevation models and astronomical software to reconstruct these sightlines, yet prehistoric builders appear to have solved the same problem using only direct observation accumulated over generations. Perhaps the most controversial aspect of Kokino concerns the moon rather than the sun. Several researchers have argued that certain rock markers correspond not only to annual solar events but also to the major lunar standstill, a phenomenon occurring approximately every 18.6 years when the moon reaches its most extreme rising positions on the horizon. Unlike the predictable annual movement of the sun, this cycle unfolds so slowly that a single observer would witness only a handful of complete repetitions during an entire lifetime. Recognizing such a pattern would require observations extending across decades, systematic transmission of knowledge between generations, or some method of preserving astronomical records that has never been discovered at the site. No inscriptions, written calendars, or symbolic diagrams have been found to explain how such information could have been maintained, leaving the hypothesis both fascinating and deeply controversial. At the center of these alignments sits the feature commonly known as the stone throne, carved directly into the volcanic rock. Although the name suggests royal authority, there is no archaeological evidence identifying it as the seat of a ruler. Instead, its importance lies in its position. The proposed astronomical alignments function most accurately when viewed from this precise location, leading some researchers to argue that it served as the principal observation point during ceremonial or calendrical events, whether occupied by a priest, an astronomer, a community leader, or someone whose role has long vanished from history remains completely unknown. No associated palace, administrative complex, or monumental architecture has ever been identified nearby, making the throne's true purpose one of Kokino's enduring mysteries. The mountain itself contributes another layer to the puzzle because its volcanic geology naturally produces fractures, fissures, and narrow openings. Critics therefore argue that many of the so-called astronomical markers may simply be natural formations selected after the fact because they happen to align with celestial events. This criticism is significant because humans have an extraordinary tendency to recognize meaningful patterns even where none were intentionally created. Supporters of the observatory hypothesis respond that the statistical probability of multiple independent alignments converging on the same observation point is far lower than random chance would predict, especially when some notches exhibit evidence suggesting deliberate modification. Even after years of study, neither interpretation has achieved universal acceptance. The absence of written evidence makes resolving the debate exceptionally difficult. Unlike Egypt or Mesopotamia, Kokino has yielded no inscriptions identifying its builders, no astronomical diagrams, no carved symbols describing rituals, and no records explaining why particular points on the horizon mattered. Archaeologists must reconstruct the site's function entirely through spatial relationships, artifact distribution, and astronomical simulation. Every new survey refines the geometry with greater precision, yet each improvement also exposes new uncertainties regarding the intentions of the people who shaped the mountain almost 4,000 years ago. Modern technology has only deepened the mystery rather than eliminating it. Satellite positioning, laser surveying, three-dimensional terrain models, and astronomical software allow researchers to calculate sunrise and moonrise positions with extraordinary accuracy, revealing that several proposed alignments are indeed remarkably close to expected celestial events. At the same time, these same technologies also demonstrate how sensitive the system is to observer position, horizon elevation, and slight measurement errors. A marker appearing convincing from one location may lose all astronomical significance from another, only a short distance away. Consequently, the debate has shifted away from whether alignments exist toward the more difficult question of whether prehistoric people intentionally designed them. Recognition beyond the archaeological community came in 2005 when NASA mentioned Kokino among notable ancient observatory sites in educational material, discussing humanity's long history of observing the sky. The reference greatly increased international attention, but it also generated a persistent misconception that NASA had officially confirmed Kokino as a fully established prehistoric observatory. In reality, the agency did not authenticate that interpretation, and the site's function remains an active subject of archaeological investigation rather than a settled scientific conclusion. In 1749, the Cornish antiquarian William Borlase recorded a small group of granite stones on the open moorland of the Penwith Peninsula in western Cornwall, England, approximately 5 kilometers northwest of the village of Madron. The monument was already ancient when he drew it, yet his plan immediately revealed something unsettling. The stones did not stand in the straight line seen today. Instead, they formed an angle of roughly 135 degrees, suggesting that the present arrangement may be partly modern and that the geometry now visible at Menon Toll is only a distorted fragment of its original design. The name Menon Toll comes from Cornish and means the hold stone. At the center stands a circular granite slab set upright on its edge. It measures approximately 1.3 meters across and about 0.3 meters thick, while the opening through its center is close to 0.5 meters in diameter. Two upright stones, each around 1.2 meters high, now stand on opposite sides of it, creating the appearance of a deliberately constructed sightline through the circular opening. Nearby are another upright stone, several fallen or partly buried stones, a low cairn, and additional prehistoric burial mounds. Historic England dates the broader monument type from the late Neolithic to the Middle Bronze Age, placing its possible construction somewhere between roughly 3000 and 1000 BCE, although no direct dating sample has yet established exactly when the hold stone was raised. Its geometry appears simple, but almost every part of it raises a question. Granite is an extremely hard crystalline rock, and the central opening passes completely through a slab thick enough to resist casual fracture. The hole is not a mathematically perfect circle, yet its broadly rounded form and relatively even internal boundary appear too regular to dismiss without explanation. Archaeologists cannot determine whether the opening was entirely artificial, whether a naturally weathered cavity was enlarged, or whether the stone was selected because the hole already existed. No workshop, discarded stone tools, or securely associated debris has been found to reconstruct the process. If prehistoric workers deliberately enlarged the opening, they had to remove material without splitting the remaining ring, whose narrowest sections carried the weight of the slab while it was lifted and set upright. The problem becomes more difficult because the stone may not have been designed for its current position. Borlase reported that local farmers had already removed stones from the surrounding ground, and later studies concluded that at least one of the surviving uprights had been moved after the early 19th century. The modern straight alignment therefore cannot automatically be treated as prehistoric. What now resembles a carefully constructed axis may be the result of restoration, agricultural disturbance, or an attempt to make the monument appear more orderly. This uncertainty destroys the simplest method of interpreting the site, because any theory based on its present orientation must first prove that the stones still occupy their original locations. Survey work has suggested that the scattered stones may once have formed part of a circle containing approximately 18 to 20 uprights. If that reconstruction is correct, Menantol was not originally a group of 3 stones, but a much larger geometric enclosure. The surviving circular slab may have stood within or beside that ring, possibly framing a point on the horizon. Yet this interpretation remains hypothetical, because most of the supposed circle has disappeared. The surviving stones are irregularly spaced, and no continuous foundation trench confirms the complete circumference. A few displaced blocks can support several incompatible reconstructions, each producing a different center, diameter, and orientation. The hold slab itself may also have belonged to an entirely different monument. Some archaeologists have compared it with perforated entrance stones used in prehistoric chambered tombs, raising the possibility that it once formed part of a portal through which the dead, offerings, or ritual participants symbolically passed. A low cairn lies immediately southeast of the present stones, while other early Bronze Age cairns stand within approximately 150 meters. The slab could therefore have been removed from a ruined burial structure and later erected among the standing stones. This would mean that the apparent geometry of Menantol combines elements from 2 monuments built for separate purposes and perhaps at different times. However, the opening is large enough for a person to crawl through, which has preserved another possibility. For centuries, local traditions claimed that passing through the stone could cure children suffering from rickets, relieve pain in the back or limbs, improve fertility, or protect against misfortune. Some rituals required a person to pass through the opening a specific number of times, or to move in a particular direction around the monument. These practices were recorded long after prehistory, so they cannot be treated as evidence of the builder's intentions. Even so, their repeated association with bodily passage suggests that the whole naturally functions as more than decoration. It creates a controlled threshold, reducing movement through the monument to a single narrow circular route. That threshold may explain why the stone has often been interpreted as a representation of birth, death, or renewal. A person approaching one side sees the landscape compressed into a circular frame, disappears briefly within the thickness of the granite, and emerges on the opposite side. The physical experience is governed by geometry. The diameter restricts posture, the ring isolates the body from the surrounding space, and the line of sight centers attention on whatever lies beyond the opening. Whether this effect was used for healing, initiation, funerary ritual, or seasonal ceremony remains unknown, but it appears too spatially powerful to ignore. The most controversial theory is that the whole served as a prehistoric viewing device. When a fixed opening is combined with a distant marker, it can define a precise visual axis toward a sunrise, sunset, lunar event, or prominent landmark. Britain contains confirmed examples of prehistoric monuments whose orientations relate to the movement of celestial bodies, so the general idea is archaeologically plausible. Yet Menantol provides no secure alignment, because its stones have been moved, and the original horizon may have been altered by vegetation, erosion, and later land use. Without knowing the prehistoric position of the circular slab, almost any apparent solar or lunar correspondence can be produced by selecting a convenient observation point. Its location nevertheless places it within an unusually dense ritual landscape. The main Skrifa standing stone lies only about 300 meters to the north, while the Boskidnan stone circle stands less than 1 kilometer to the northeast. Cairns, barrows, quoits, and other standing stones occupy the surrounding moor. This concentration suggests that prehistoric communities were not placing monuments in isolation, but organizing them across a landscape already filled with ancestral and ceremonial meaning. Menontoul may therefore have operated as one geometrical component within a much larger network of routes, sightlines, and sacred zones, although archaeology has not demonstrated a unified plan connecting them. What survives today is consequently deceptive. The circular stone appears complete, the flanking uprights appear aligned, and the monument seems easy to understand at a glance. In reality, its original circumference, orientation, chronology, and function are all uncertain. The whole may be natural or modified, the slab may be a tomb entrance or a central marker, and the visible straight line may never have existed in prehistory. Even the estimated age covers more than 1,000 years of profound cultural change. Northwestern Tunisia. A mountain of golden marble supplied some of the greatest monuments of the Roman Empire. More than 2,000 years later, archaeologists still debate how ancient engineers extracted, shaped, polished and transported stone on an industrial scale without modern machinery. Ancient Chemtu, known in antiquity as Simithus, was identified through archaeological investigations beginning in the 19th century. Excavations later revealed vast quarry complexes, workshops, roads, hydraulic systems, and evidence of one of the largest marble industries in the Roman world. Chemtu was unlike most ancient cities because its importance came from the mountain itself. The site contained deposits of Numidian marble, known to the Romans as *Giallo Antico *. Characterized by striking yellow, gold, and reddish veining, it became one of the most valuable decorative stones in the empire. Ancient authors described it as a luxury material reserved for imperial projects, temples, and elite architecture. What makes this remarkable is its distribution. Marble from Chemtu has been identified hundreds and sometimes thousands of kilometers from its source. It appeared in Rome, Ostia, and numerous provincial cities throughout the Mediterranean. Today, transporting a single 50-ton stone block requires heavy trucks, cranes, specialized permits, and carefully planned logistics. Yet Roman engineers moved enormous quantities of marble across an empire spanning more than 5 million square kilometers. The first mystery is simple. How did a quarry located deep inside North Africa become one of the primary suppliers of decorative stone for an empire stretching across 3 continents? At first glance, quarrying appears straightforward. Remove stone from a mountain and transport it elsewhere. In reality, the process is far more complicated. Modern quarry operations rely on diamond wire saws, hydraulic splitters, explosives, and computerized cutting systems. Yet Roman quarry workers possessed none of these technologies. Even so, evidence from Chemtu demonstrates that workers extracted blocks weighing tens of tons with surprising precision. Archaeologists have documented quarry faces containing long, straight extraction channels. These grooves reveal careful planning and highly controlled cutting methods. Workers likely used iron tools, wedges, hammering techniques, and systematic fracture control. The challenge is understanding how they avoided catastrophic failures. Stone is unpredictable, and hidden fractures can destroy months of work instantly. Modern engineers use geological surveys and advanced imaging technologies to identify weaknesses before cutting begins, while ancient quarry workers relied entirely on observation and experience. Even today, experimental archaeologists attempting to reproduce ancient quarrying techniques often discover that apparently simple methods require extraordinary skill. Small mistakes can split a block incorrectly, reducing its value dramatically. Chem2 suggests generations of accumulated practical knowledge that was rarely written down and has largely disappeared. Perhaps the most astonishing achievement was not quarrying but transportation. Some marble blocks likely weighed between 20 and 60 tons, while larger examples may have exceeded 100 tons. To understand the scale, consider that an African elephant weighs roughly 6 tons. A 60-ton marble block therefore weighed approximately as much as 10 adult elephants combined. The blocks first had to be moved from the quarry itself. They then travelled toward river systems, reached ports, crossed portions of the Mediterranean Sea, and finally arrived at construction sites. Roman engineers achieved this without diesel engines, hydraulic cranes, steel cables, or modern roads. Researchers estimate that moving large stone blocks often required hundreds of workers, specialized sledges, rollers, lifting devices, and carefully organized labor systems. The mystery is not whether the Romans transported these stones, because the marble survives as proof. The mystery is how they accomplished the process so efficiently and repeatedly for centuries. Before extraction could begin, quarry managers needed to understand the mountain. Not every section of marble possessed the same quality. Decorative stone was valuable because of its color consistency, structural integrity, and visual appearance. Modern geologists use seismic imaging, ground-penetrating radar, and three-dimensional modeling to locate promising deposits. Ancient quarry workers possessed none of these technologies, yet they repeatedly targeted areas containing some of the most visually attractive marble available. How they identified the best sections remains uncertain. Some researchers believe Roman quarry specialists developed sophisticated observational techniques based on surface patterns, fracture behavior, coloration, and geological experience accumulated across generations. If true, much of this knowledge disappeared with the collapse of the Roman industrial system. Of all Chem2's technological puzzles, none may be more fascinating than what happened after extraction. Cutting stone was only the beginning. The true challenge was transforming rough marble into polished architectural masterpieces capable of decorating imperial buildings. Visitors to Roman monuments often focus on columns, statues, and architectural grandeur, yet the surfaces themselves represent a technological achievement that remains surprisingly difficult to explain in detail. Many surviving examples of Numidian marble exhibit extraordinarily smooth finishes. Even after nearly 2,000 years, some surfaces continue reflecting light with remarkable effectiveness. Creating such finishes requires removing microscopic imperfections from the stone. Modern stone processing facilities accomplish this through electrically powered polishing systems using carefully engineered abrasives. Computer-controlled machinery applies consistent pressure while rotating polishing heads gradually refine the surface. Ancient craftsmen possessed none of these tools, yet they achieved results that still impress modern conservators. Researchers believe workers employed a sequence of increasingly fine abrasives. Quartz sand, emery, crushed minerals, and specialized polishing compounds have all been proposed. The problem is that no complete ancient technical manual survives explaining the exact process. Experimental archaeology has produced intriguing results. Teams attempting to recreate Roman polishing techniques discovered that achieving mirror-like finishes can require enormous amounts of labor. Hours become days, and days become weeks. The process demands not only materials but also highly developed expertise. Pressure must be carefully controlled, the abrasive sequence must be correct, and surface irregularities must be identified and removed. Even slight mistakes can ruin the final appearance. This raises a fascinating possibility. Perhaps the most valuable resource at Chem2 was not marble itself, but skilled human knowledge. A master stone finisher may have possessed techniques acquired through decades of apprenticeship. Such knowledge could have been transmitted directly from craftsman to craftsman without ever being formally documented. If that transmission chain breaks, the knowledge disappears. This pattern appears repeatedly throughout history. The formula for Roman marine concrete remained poorly understood for centuries. The manufacturing techniques behind Damascus steel continue generating debate. The mechanisms used to construct certain megalithic monuments remain controversial. Chem2 may belong to the same category. The marble survives, but the craftsmen do not, and with them may have vanished some of the most sophisticated practical knowledge of the ancient world. Chem2 was far more than a local quarry. Large extraction areas, workshops, transport networks, and worker settlements reveal a vast, organized industry. Managing labor, supplies, transportation, and quality control without modern technology required remarkable coordination. That this system operated successfully for centuries remains one of the great achievements of the ancient world. What do you think? Were the achievements of Chem2 simply the result of generations of accumulated experience? Or did its craftsmen possess specialized technological knowledge that has largely been lost to history? Let us know your thoughts in the comments below. Central Nigeria. Thousands of years ago, deep inside a landscape of caves and rocky hills, a civilization appeared that could smelt iron, create life-size sculptures, and organize large-scale production long before many neighboring societies entered the Iron Age. Yet they left no written language, no engineering manuals, and no explanation, only mysteries. Today, the Nok Cave complex remains one of the most intriguing archaeological puzzles in Africa, raising a question that still challenges researchers. How advanced was the lost technology of the Nok people? The Nok civilization was first identified in 1928 when miners searching for tin in central Nigeria unexpectedly uncovered unusual terracotta sculptures buried beneath the soil. Subsequent excavations revealed a much larger culture dating between approximately 1500 BC and 500 AD. Archaeologists later discovered caves, habitation sites, furnaces, iron artifacts, pottery workshops, and hundreds of terracotta fragments scattered across a vast region exceeding 70,000 square kilometers. What emerged was evidence of one of the earliest complex societies in sub-Saharan Africa, but the discoveries created more questions than answers. Among all Nok achievements, none are more astonishing than the terracotta figures. Many stand nearly 1 meter tall, and some depict human beings with elaborate hairstyles, jewelry, facial expressions, and geometric designs so precise that they appear almost modern. The sculptures are typically hollow, suggesting their creators understood structural stresses during firing. This may sound ordinary today, but it was not. Large clay sculptures are extremely difficult to manufacture. As moisture escapes during drying and firing, internal stresses develop. If the walls are too thick, the sculpture can explode. If they are too thin, it can collapse. Uneven heating creates fractures, while poor clay composition leads to deformation. Modern ceramic artists use controlled kilns, thermometers, and carefully refined materials to reduce these risks. The Nok people possessed none of these technologies, yet many sculptures survived. This raises one of the greatest technological mysteries of ancient Africa. How did they achieve such consistency? Researchers believe Nok artisans intentionally selected specific clay deposits with favorable mineral compositions. Some analyses suggest the clay was carefully prepared before shaping, indicating an understanding of material properties developed through generations of experimentation. Even more impressive is the artistic standardization. Across hundreds of kilometers, sculptures display similar stylistic characteristics. Eyes are often represented by triangular or circular openings. Facial proportions follow recurring patterns, and decorative motifs appear repeatedly. Such consistency suggests either extensive communication between communities or specialized craftsmen transmitting knowledge across generations. The comparison with other ancient civilizations is striking. The famous terracotta warriors of China date to the 3rd century BC, yet many Nok sculptures may be centuries older. Unlike the Chinese figures, however, the Nok statues were produced without imperial workshops, written instructions, or centralized bureaucracies that we know of. The knowledge system responsible for their production remains almost completely invisible, and that is perhaps the greatest mystery. The sculptures survived, but the technology behind them did not. The Nok culture is frequently associated with some of the earliest evidence of iron production in sub-Saharan Africa. This discovery transformed archaeological understanding of African technological history. Producing iron is not a simple task. Iron ore must be heated to temperatures approaching 1,200 degrees Celsius, and achieving such temperatures requires sophisticated control of furnace design, airflow, fuel quality, and ore selection. Even modern experimental archaeologists struggle to reproduce ancient iron-working techniques without extensive preparation. Excavations have uncovered furnace remains, slag deposits, and iron artifacts indicating sustained metallurgical activity. The volume of slag found at certain sites suggests production occurred on a scale far beyond occasional toolmaking. Yet no written records explain how Nok metalworkers mastered this process. One of the biggest debates concerns the origin of the technology itself. Did Nok communities independently develop iron smelting, or was the knowledge introduced through long-distance cultural exchange? Decades of research have failed to provide a definitive answer. If independent invention occurred, the Nok people achieved one of humanity's most important technological breakthroughs entirely on their own. Technology rarely exists in isolation. Iron production requires miners, terracotta production requires clay specialists, large communities require food producers, and trade requires organization. The Nok archaeological landscape reveals evidence of all these activities. What remains unclear is how such knowledge was transmitted. Without writing, technical information had to pass orally. Generations of craftsmen may have spent decades mastering techniques before teaching apprentices. Entire technological systems could therefore disappear if social structures collapsed. This possibility may explain why so much Nok expertise seems lost today. We can see the products, but we cannot see the instructions. The caves themselves present another puzzle. Archaeologists have discovered evidence suggesting that some caves were occupied, while others may have served ceremonial functions. Certain locations contain pottery fragments, charcoal deposits, and artifacts indicating repeated human activity. Yet many caves occupy difficult positions that offer little practical advantage for daily living. This has led researchers to propose alternative explanations. Perhaps the caves served as ritual centers. Perhaps they functioned as refuges during conflict. Perhaps they stored valuable resources. Or perhaps they played multiple roles over centuries. The available evidence remains incomplete, and as a result, the true purpose of many Nok cave sites is still debated. One often overlooked mystery concerns organization. The Nok cultural area covered tens of thousands of square kilometers. Maintaining artistic traditions across such distances would have required communication networks, movement of people, and shared cultural standards. Today, similar coordination depends on roads, telecommunications, and written administration. The Nok people possess none of these systems as far as current evidence shows, yet their cultural identity remained remarkably consistent. How information moved across this landscape remains largely unknown. Around the middle of the first millennium AD, the Nok culture gradually vanished from the archaeological record. no evidence points to a single catastrophic event. No massive battlefield has been discovered, and no definitive proof of epidemic collapse exists. Climate change, environmental pressures, migration, and social transformation have all been proposed, but none fully explain the disappearance. The result was the loss of one of Africa's earliest technological traditions. Knowledge accumulated over centuries simply faded from history. What do you think? Were the Nok people simply master craftsmen, or did they possess technological knowledge that was centuries ahead of their time? Share your thoughts in the comments below. Sijil Massa is one of the greatest lost cities of the ancient world. Located on the edge of the Sahara Desert in southeastern Morocco, this forgotten metropolis controlled one of the richest trade networks in human history. Gold from West Africa, goods from the Mediterranean, and caravans crossing thousands of kilometers of desert all converged here. Yet the city that once accumulated immense wealth vanished almost completely, leaving behind mysteries that archaeologists still struggle to explain. The ruins of Sijil Massa lie within Morocco's Tafilalt oasis. Historical descriptions survived in medieval Arabic texts, but centuries of abandonment, erosion, flooding, and human activity erased much of the city. Modern archaeological investigations beginning in the 20th century revealed traces of urban districts, irrigation systems, workshops, and evidence of large-scale commercial activity. The discoveries confirmed that Sijil Massa was not merely a desert settlement, it was one of the most important economic centers of medieval Africa. Few locations seem less suitable for sustaining a major city than the Sahara. Average annual rainfall in the Tafilalt region is often below 100 millimeters. Summer temperatures regularly exceed 40 degrees Celsius. Water is scarce, vegetation is limited, and agricultural production faces constant environmental stress. Yet historical sources describe a prosperous city surrounded by extensive palm groves and agricultural land capable of supporting tens of thousands of people. This presents a major engineering puzzle. Modern desert cities rely on pumps, pipelines, reservoirs, electrical infrastructure, and satellite monitoring systems, but Sijil Massa possessed none of these technologies. Researchers believe its survival depended on sophisticated water management systems involving canals, diversion structures, underground channels, and carefully regulated irrigation networks. However, much of this infrastructure has disappeared. Archaeologists can identify fragments of the system, but the complete design remains unknown. How engineers maintained reliable water distribution over centuries remains one of the city's greatest mysteries. The challenge becomes even more remarkable when compared to other ancient hydraulic civilizations. The Romans constructed aqueducts capable of transporting water over distances exceeding 80 kilometers, while Persian engineers developed qanat systems that tapped underground aquifers through tunnels extending for many kilometers. Sijil Massa appears to belong within this tradition of hydraulic innovation, yet its techniques remain poorly understood. Sijil Massa served as the northern gateway of the Trans-Saharan trade network. This was not a local commercial route, it was one of the largest economic systems on Earth before the modern era. Caravans often travelled more than 1,500 kilometers through some of the harshest environments on the planet. Certain journeys required several months, and thousands of camels transported gold, ivory, salt, textiles, copper, and countless other goods between North Africa and sub-Saharan kingdoms. Maintaining such a network required extraordinary logistical planning. A camel can consume significant quantities of water and food. Human travelers required supplies, trade goods had to be protected, and navigation errors could prove fatal. Yet for centuries these routes functioned with remarkable reliability. How caravan leaders navigated vast stretches of nearly featureless desert remains debated, Some scholars point to sophisticated astronomical navigation using stars, while others suggest generations of accumulated environmental knowledge involving wind patterns, dunes, geological formations, and seasonal conditions. Whatever methods were used, the achievement rivaled the navigational abilities of Polynesian sailors crossing the Pacific Ocean without modern instruments. Historical accounts indicate that Sigil Massa became one of the wealthiest cities in North Africa. Managing such prosperity required more than merchants, it required administration. Taxes had to be collected, trade had to be regulated, agricultural production had to be monitored, water distribution had to be coordinated, and security had to be maintained. Today, such functions depend on databases, communication networks, and advanced bureaucratic systems. Sigil Massa had none of these advantages, yet records suggest that the city successfully managed commercial activity involving regions separated by thousands of kilometers. The administrative knowledge behind this achievement has largely vanished. Unlike some Roman or Chinese centers where extensive documentation survives, Sigil Massa left relatively few records explaining how its institutions functioned. As a result, historians can observe the outcome but not the mechanisms that produced it. Perhaps the most overlooked technological achievement of Sigil Massa was its ability to adapt to environmental extremes. The city existed in a region vulnerable to drought, flash floods, sand encroachment, and long-term climate fluctuations. Modern climate studies indicate that relatively small changes in precipitation can dramatically affect agricultural productivity in desert environments. Yet Sigil Massa endured for centuries. Its builders developed architectural solutions using mud brick and earthen construction. At first glance, these materials appear primitive. In reality, they possess remarkable thermal properties. Thick earthen walls absorb heat during the day and release it slowly at night, reducing temperature fluctuations inside buildings. Modern sustainable architecture increasingly studies similar principles. The challenge is understanding how builders optimize these techniques without formal engineering science. The city's longevity suggests generations of accumulated knowledge that may never be fully reconstructed. Of all Sigil Massa's technological puzzles, none may be more fascinating than its relationship with gold. For centuries, West Africa supplied an enormous proportion of the world's known gold. Medieval sources suggest that major gold-producing regions south of the Sahara generated vast quantities of the precious metal. Through its strategic location, Sigil Massa became one of the principal gateways through which this wealth entered North Africa and the Mediterranean world. Gold arriving in Sigil Massa was transformed from raw material into economic power. Archaeological evidence and historical records indicate the city played a major role in gold processing, valuation, and coin circulation. This is where the mystery begins. Producing reliable gold coinage requires far more sophistication than many people realize. Gold extracted from mines rarely possesses consistent purity. Natural gold often contains varying amounts of silver, copper, and trace elements. Without proper refinement, coins can vary significantly in value. Modern metallurgical laboratories use spectrometers, chemical analysis, and precision measurement instruments. Ancient metalworkers had none of these tools. Yet medieval Islamic gold coins achieved extraordinary commercial trust across enormous distances. Merchants in North Africa, Al-Andalus, and the Mediterranean accepted these coins because they believed their gold content was reliable. How was that trust maintained? Researchers believe skilled metallurgists employed techniques involving cupellation, alloy control, repeated melting cycles, and density-based evaluation methods. The problem is that much of the practical knowledge behind these processes was rarely documented in detail. Even today, experimental archaeologists attempting to recreate ancient refining techniques often discover that seemingly simple procedures require extensive experience and precision. Small variations in furnace temperature can alter results dramatically. Maintaining temperatures above 1000 degrees Celsius demands careful control of airflow, fuel quality, furnace geometry, and ore composition. Ancient craftsmen possessed no thermometers, yet they repeatedly achieved successful outcomes. Some historians argue that master metallurgists relied upon visual cues, flame color, sound, and centuries of transmitted expertise. If true, this would represent an extraordinarily sophisticated technological tradition largely lost to history. The scale of the operation raises additional questions. Historical estimates suggest that trans-Saharan trade moved enormous quantities of gold over many centuries. Some researchers believe that during certain periods, West African sources may have supplied a substantial portion of the gold circulating throughout the Mediterranean economy. If Sigil Massa served as a major redistribution center, then its merchants and metal workers were effectively participating in one of the largest precious metal supply chains on Earth. Yet the infrastructure supporting this system remains only partially understood. Where were the refining workshops? How were purity standards enforced? How were fraudulent coins detected? How was gold securely stored, transported, and exchanged? The archaeological record provides fragments of answers, but not the complete picture. As a result, the metallurgical expertise of Sigil Massa remains one of the most intriguing unsolved technological mysteries of the medieval world. The greatest mystery may be not how Sigil Massa rose, but how it vanished. Political unrest, warfare, economic change, shifting trade routes, and environmental pressures likely all contributed to its decline. Like many ancient cities, it appears to have faded due to multiple factors, eventually disappearing beneath the sands. What do you think? Was Sigil Massa simply a successful trading city? Or did its inhabitants possess engineering and metallurgical knowledge far more advanced than historians currently understand? Let us know your thoughts in the comments below. Stone palaces, monasteries, and churches cling to the steep slopes of Mount Taygetus near Sparta, Greece, after more than 700 years of earthquakes, wars, humidity, and abandonment. But the deeper archaeologists studied Mystras, the stranger it became. Some of its engineering systems appear centuries ahead of their time, and some of its materials still behave in ways historians cannot fully explain. Although local populations always knew the ruins existed, systematic archaeological study of Mystras only accelerated during the late 19th and early 20th centuries after Greece gained independence from the Ottoman Empire. Excavations revealed something unexpected. This was not just a medieval fortress. Mystras had once been the final great intellectual and political center of the Byzantine Empire. At its peak during the 14th and 15th centuries, the city may have held more than 20,000 inhabitants spread vertically across terraces cut directly into unstable mountain terrain. Archaeologists uncovered advanced water systems, earthquake-resistant masonry, hidden cisterns, frescoes with unusual chemical durability, and palace ventilation designs that resemble passive climate control systems used in modern sustainable architecture. The greatest mystery of Mystras may not be its walls or palaces, but its paintings. Inside churches like the Pantanassa Monastery and the Church of Peribleptos, Byzantine frescoes painted between the 13th and 15th centuries still retain remarkable reds, blues, gold tones, and facial detail despite centuries of smoke, candle soot, earthquakes, moisture, fungal growth, and temperature fluctuation. In many sections, the pigments appear dramatically better preserved than frescoes of comparable age elsewhere in Europe. Scientists studying Byzantine wall paintings discovered that many pigments used at Mistras were based on iron oxides, copper minerals, lime compounds, carbon blacks, and naturally stabilized earth pigments. Those materials alone do not fully explain the preservation. The larger mystery lies in the plaster beneath them. Microscopic analysis of Byzantine lime plaster from similar Greek sites has shown extremely dense crystalline bonding caused by slow carbonation processes. In some areas, the plaster behaves almost like a mineral shell, trapping pigments beneath a hardened, breathable surface. Modern conservation experts compare this effect to self-stabilizing mineral coatings used in advanced restoration science today. Even stranger, some fresco layers at Mistras show unusually low salt damage despite the Mediterranean climate. Salt crystallization is one of the primary reasons ancient wall paintings decay. At sites across Italy and the Middle East, salt expansion slowly destroys painted surfaces from inside the wall. Yet several Mistras frescoes survived with minimal structural flaking. One theory suggests Byzantine artisans may have intentionally mixed volcanic ash, ceramic dust, or finely crushed fired clay into the plaster, creating hydraulic reactions similar to Roman pozzolanic concrete. That would allow the walls to regulate moisture more efficiently while resisting cracking. Similar techniques helped Roman harbours survive for nearly 2,000 years underwater. Comparisons with medieval European frescoes are striking. Many 14th century paintings in humid regions of France or England lost large portions of their pigment within only a few centuries, yet some faces and robes at Mistras remain visible with extraordinary clarity after over 600 years. Researchers also noticed something unusual about the placement of the paintings themselves. Certain church interiors were designed to minimize direct sunlight and stabilize humidity. Narrow windows filtered light in ways that reduced ultraviolet damage while still illuminating key religious imagery. In modern museum preservation, similar principles are deliberately engineered using climate-controlled lighting systems. The mystery deepens because Byzantine technical manuals describing pigment preparation from this period are extremely limited. Much of the practical knowledge may have vanished after the fall of Constantinople in 1453. If master craftsmen at Mistras possess specialized formulas for stabilizing pigments and plaster, those recipes may have disappeared forever. Mistras stands in one of the most seismically active regions in Europe. Southern Greece experiences frequent tectonic activity due to interactions between the African and Eurasian plates. Over centuries, the region endured repeated earthquakes powerful enough to destroy ordinary medieval structures. Yet large portions of Mistras survived. Architectural studies found that many buildings used alternating layers of stone and thin brick bands, a Byzantine technique that distributed seismic stress more evenly across walls. Instead of rigidly resisting earthquakes, the structures could absorb and dissipate vibration. Some foundations also incorporated softer mortar zones between heavy stone blocks. Modern earthquake engineering sometimes uses flexible joints and dampening layers for similar reasons. What makes this remarkable is the terrain itself. Mistras was built vertically across steep mountain slopes vulnerable to erosion and landslides. Even modern hillside construction requires deep geological analysis and reinforced retaining systems. Medieval engineers achieved structural stability using little more than stone lime mortar geometry and experience. Comparisons with other medieval cities are revealing. Numerous castles in Western Europe collapsed after centuries of soil movement and seismic activity. Yet sections of Mistras remain standing despite being built on terrain that modern engineers would consider highly unstable. Supplying water to a mountainside city should have been nearly impossible. But Mistras maintained fountains, monasteries, baths, gardens, and residential districts for generations. Archaeologists discovered hidden cisterns, underground channels, terracotta pipelines, and carefully graded water routes carved into the slope itself. The system relied entirely on gravity and pressure balance. Even a small miscalculation in angle could have stopped water flow or caused destructive erosion. Modern hydraulic engineers note that maintaining stable flow across vertically layered settlements without pumps requires extremely precise understanding of gradient control. Some channels were concealed within walls to protect them during sieges. Others distributed overflow water into agricultural terraces below the city, reducing waste while preventing slope instability. Compared to many medieval European cities that struggled with contaminated wells and sewage outbreaks, Mystra's appears unusually advanced in water management. The Palace of the Despots contains another mystery rarely discussed outside architectural studies. During summer, some internal chambers remain noticeably cooler than surrounding exterior areas. Researchers believe the palace used a passive thermal regulation system based on airflow, wall thickness, shaded courtyards, and mountain wind circulation. Narrow openings accelerated airflow through pressure differences, while thick masonry slowed heat transfer during the day. This resembles principles used in modern passive cooling architecture and sustainable environmental design. Similar concepts appear in Persian wind catchers and ancient desert cooling towers, but Mystra's adapted them to a mountainous Mediterranean environment. The design becomes even more surprising considering the Byzantine Empire was already in political and economic decline during Mystra's golden age. Despite that instability, engineers and architects were still applying highly sophisticated environmental design principles. What do you think is the biggest mystery of Mystra's? The earthquake-resistant engineering, the advanced water systems, or the frescoes that somehow refuse to fade for centuries? Let us know in the comments below. Buried beneath the hills of northern Greece near the modern village of Vergina, royal tombs of Aigai remained untouched for more than 2,300 years. Then archaeologists opened the chambers and discovered gold, paintings, weapons, and engineering techniques that still do not fully make sense today. The discovery happened in 1977, when Greek archaeologist Manolis Andronikos excavated a massive burial mound believed to hide the ancient Macedonian capital of Aigai. Beneath layers of earth, he uncovered sealed royal tombs that many historians believe belonged to King Philip II, father of Alexander the Great. What shocked researchers was not only the wealth inside, but how perfectly preserved everything remained. Unlike most ancient tombs looted long ago, these chambers appeared almost frozen in time. The deeper scientists studied Aigai, the stranger the sight became. Most ancient Macedonian tombs were destroyed by grave robbers or collapsed from moisture and earthquakes, yet Tomb 2 at Aigai survived in remarkably stable condition for over 2 millennia. The chamber maintained enough environmental stability to preserve organic materials, painted surfaces, and delicate gold artifacts. Researchers discovered that the tomb walls were coated with a highly refined lime-based plaster capable of regulating humidity. Modern analysis suggests the material behaved similarly to breathable mineral coatings used in advanced conservation architecture today. The plaster absorbed excess moisture during humid periods and slowly released it during dry conditions, reducing internal condensation. This is extraordinary because northern Greece experiences major seasonal humidity swings. Temperatures can range from below freezing in winter to over 35 degrees C in summer. Under those conditions, most sealed underground chambers accumulate water damage rapidly. Yet the paintings and burial goods inside Aigai remained unusually intact. Some engineers compare this environmental control system to the microclimate preservation seen inside certain Egyptian tombs, but Egypt relied heavily on desert dryness. Aigai existed in a much wetter environment. That difference makes the Macedonian achievement far harder to explain. The murals inside the tombs became one of the greatest archaeological surprises of the 20th century. Ancient Greek panel paintings are almost completely lost to history, meaning the frescoes at Aigai offered one of the first direct looks at Greek painting techniques described by classical writers. One hunting scene stretched across the tomb facade with astonishing detail and movement. The pigments retained reds, blacks, blues, and ochre tones, despite more than 3,300 years underground. Scientific studies identified minerals such as cinnabar, hematite, Egyptian blue, and carbon black. But the true mystery lies in the preservation layer. Microscopic analysis revealed evidence of an ultra-thin protective coating applied over parts of the artwork. Some researchers believe Macedonian artists used a mineral organic sealant capable of slowing oxidation and stabilizing pigments. The formula remains uncertain because surviving traces are extremely degraded. Compared to Roman wall paintings at Pompeii Archaeological Park, the Aigai paintings display more advanced anatomical motion and perspective despite being centuries older. Some art historians argue these murals prove that Greek painters had already mastered techniques that Europe would not fully rediscover until the Renaissance. The greatest mystery inside Aigai was the gold larnax, a ceremonial coffin crafted from nearly pure gold and decorated with a 16-rayed vagina sun symbol. At first glance, the object appears impossibly precise for a 4th century BCE workshop. The coffin weighs roughly 11 kilograms and was hammered into shape using thin sheets of high-purity gold. Modern metallurgical analysis showed that many sections maintain nearly uniform thickness, despite being manually formed. Even more astonishing are the microscopic engraved patterns surrounding the solar emblem. The symmetry is so exact that some experts initially assumed rotational measuring tools must have been used. Ancient Macedonian craftsmen were not supposed to possess that level of metallurgical consistency. To create a structure this delicate without cracking the metal, artisans would have needed extraordinary temperature control during repeated heating and hammering cycles. Gold becomes brittle if improperly cooled, especially when worked into thin, ceremonial panels. Yet the Aigai larnax shows almost no major stress fractures. Researchers believe the craftsman likely used advanced annealing techniques, carefully reheating the metal between shaping stages to maintain flexibility. The problem is that maintaining stable furnace temperatures above 600 GC with ancient charcoal systems should have been extremely difficult. Some experimental archaeologists attempted to reproduce the coffin using reconstructed ancient tools. Many replicas developed warping, uneven compression, or fracture marks absent from the original artifact. Even the decorative rosettes remain controversial. Certain engraved sections contain line precision measured in fractions of a millimeter. Under magnification, some cuts appear astonishingly clean for hand-driven bronze or iron tools. Historians debate whether unknown polishing compounds or ultrafine abrasive sands were involved. The mystery becomes even deeper when compared to Persian and Egyptian royal goldwork of the same era. While those civilizations produced magnificent jewelry, the Aigai coffin demonstrates an unusual balance between structural geometry and artistic precision. It feels less like jewelry and more like engineered ceremonial architecture. No surviving Macedonian text explains how such objects were manufactured. The tombs themselves also display engineering knowledge far beyond what many historians expected from the Macedonian kingdom. The vaulted chambers distribute weight using carefully angled stone blocks that redirect pressure away from the central roof span. Some structural engineers comparing the tomb to later Roman vaulting systems noted that the Macedonians appear to have understood load transfer surprisingly well. Massive limestone blocks were fitted together with minimal gaps. Even after centuries of seismic activity in the Balkans, large sections remained stable. Laser scans revealed deviations in stone alignment smaller than a few millimeters in some areas. One theory suggests builders intentionally designed slight inward inclines within the chamber walls to resist lateral earth pressure from the burial mound above. Similar stabilization principles are used in modern retaining structures. This matters because the tombs were buried beneath thousands of tons of compacted earth. A failure in weight distribution would have collapsed the chambers long ago. Some archaeologists suspect the tomb entrances were aligned with seasonal sunlight patterns tied to royal burial rituals. Computer simulations suggest sunlight may once have entered the tomb corridor at specific solar angles during certain times of year, briefly illuminating the burial chamber interior. If accurate, the builders possessed a sophisticated understanding of solar movement. This type of astronomical alignment is often associated with monuments like Stonehenge or Newgrange, but Aigai is different because the chambers were hidden beneath artificial burial mounds, making light control dramatically more difficult. The possibility that Macedonian architects intentionally integrated symbolic solar illumination into underground royal tombs remains one of the site's most debated mysteries. Even today, scholars still argue about who was truly buried inside Tomb 2. Most evidence points toward Philip II. Ancient records describe the king suffering a leg injury and eye trauma during battle, and skeletal analysis revealed injuries consistent with those accounts. But some researchers argue the remains could belong to Philip III Aridaeus instead. Radiocarbon analysis, cremation studies, and forensic reconstruction have produced conflicting interpretations. If the tomb belongs to a different ruler, historians may need to rethink large portions of Macedonian royal burial chronology. That uncertainty transforms Aigai from a solved archaeological discovery into an active historical mystery. Do you think the tomb truly belonged to Philip II? Or could history have identified the wrong king for centuries? Share your thoughts in the comments below. Northern Tunisia. Beneath the ruins of an ordinary-looking Roman city lies one of the most extraordinary engineering mysteries of the ancient world. At Bulla Regia, wealthy residents did something almost unimaginable. Instead of building upward, they built downward. Entire luxury homes were constructed beneath the ground, complete with bedrooms, dining halls, courtyards, fountains, and some of the finest mosaics ever discovered in North Africa. Nearly 2,000 years later, archaeologists can still walk through these underground villas. What they still cannot fully explain is how ancient builders created a system so advanced that many of its engineering principles resemble modern climate-controlled architecture. Although local ruins had been known for centuries, systematic excavations began during the late 19th and early 20th centuries under French archaeologists. What they uncovered shocked researchers. Beneath the visible ruins were entire residential levels preserved underground. As excavation continued, more subterranean villas emerged, revealing a city unlike almost any other in the Roman world. Today, Bulla Regia is considered one of the best preserved examples of Roman domestic architecture ever discovered. Yet preservation is only part of the mystery. Most Roman cities followed the familiar pattern, with houses, forums, baths, and temples constructed above ground. Bulla Regia was different. Many of its elite residences included complete underground living quarters, extending several meters below the surface. At first glance, the explanation seems obvious. Tunisia experiences extremely hot summers, and modern temperatures in the region frequently exceed 40 degrees Celsius. But solving a climate problem and constructing an entire underground residential system are two very different things. Modern underground buildings require careful calculations involving thermal transfer, ventilation, structural stability, drainage, and moisture control. Ancient builders possessed no computers, no climate simulations, and no engineering software. Yet they successfully created underground spaces capable of remaining habitable for centuries. Researchers studying subterranean architecture have found that soil temperatures several meters below the surface often remain significantly more stable than air temperatures above ground. In many regions, underground temperatures fluctuate only a few degrees throughout the year. The builders of Bulla Regia somehow understood this principle almost 2 millennia before modern environmental engineering. The question is how. One of the greatest mysteries involves temperature regulation. Modern architects increasingly use passive cooling systems to reduce energy consumption. Such systems rely on thermal mass, airflow, shading, and underground temperature stability. Bulla Regia appears to have implemented many of these principles long before the invention of electricity. Thick stone walls absorbed heat slowly, underground chambers remained naturally cool, courtyards allowed sunlight while limiting overheating, and carefully placed openings encouraged air circulation throughout the structure. Today, these concepts are taught in architectural engineering programs. Yet no surviving Roman document explains exactly how builders at Bulla Regia optimized these designs. Were they following mathematical rules? Were they relying on generations of accumulated experience? Or did they possess practical environmental knowledge that has largely disappeared from history? No one knows. Perhaps the most astonishing mystery of all lies beneath visitors' feet. The underground villas contain some of the most spectacular Roman mosaics ever discovered, and many remain remarkably intact despite spending centuries below ground. This should not have happened. Mosaics are fragile engineering systems. Each artwork consists of thousands, sometimes millions, of carefully arranged tesserae embedded within multiple layers of mortar and foundation material. For a mosaic to survive, the underlying structure must remain stable. Even minor shifts can produce cracks, moisture can weaken mortar, ground pressure can deform surfaces, and temperature changes can accelerate deterioration. Yet many mosaics at Bulla Regia survived with extraordinary clarity. Some still preserve intricate mythological scenes, geometric designs, marine imagery, and detailed human figures nearly 2,000 years after their creation. The technical challenge becomes even more remarkable when considering where these mosaics were built. They were not installed in open-air courtyards. Many were placed deep underground. How did Roman craftsmen achieve such precision in enclosed subterranean spaces? Lighting presents one mystery. Modern mosaic restoration projects often require powerful artificial illumination, while ancient artisans possessed only daylight, oil lamps, and reflective surfaces. Yet the mosaics demonstrate astonishing accuracy. Another mystery involves leveling. Large mosaic floors require exceptionally flat foundations, and modern builders use laser instruments capable of measuring millimeter-scale variations. Roman craftsmen possessed none of these technologies. Nevertheless, many floors remain remarkably level after nearly 20 centuries. Then there is the problem of moisture. Underground environments naturally accumulate humidity, and water infiltration is among the greatest threats to ancient mosaics. Yet numerous examples at Bulla Regia survive far better than mosaics exposed to open weather elsewhere in the Mediterranean. Some researchers believe the underground environment acted as a protective chamber, shielding the artworks from ultraviolet radiation, temperature extremes, storms, and human activity. Others argue that sophisticated drainage systems may have played a crucial role. The truth remains uncertain. What is certain is that these mosaics challenge assumptions about ancient construction capabilities. Their survival represents not merely artistic achievement, but a remarkable triumph of engineering. Any underground structure faces a fundamental problem: air. Without sufficient ventilation, carbon dioxide accumulates, humidity rises, mold spreads, and living conditions deteriorate rapidly. Yet Bulla Regia's underground residences functioned as comfortable living spaces. Archaeologists have identified courtyards, openings, stairwells, and architectural features that may have encouraged airflow. Some researchers propose that the villas exploited natural convection currents. Warm air rises while cool air sinks. If openings are carefully positioned, a building can effectively ventilate itself. Modern architects still use this principle, but determining the exact airflow behavior within Bulla Regia remains difficult because much of the original superstructure has disappeared. What survives may represent only part of a much larger system. Modern basements frequently suffer from water damage despite advanced materials and technology. Bulla Regia presents the opposite problem. Why did so many underground structures survive? Roman builders were famous for their mastery of lime mortars and hydraulic construction materials. However, the precise methods used at Bulla Regia remain uncertain. Excavations suggest careful attention to drainage, foundation preparation, and wall construction. Yet researchers still debate how these systems performed so effectively over such long periods. The question resembles ongoing investigations into Roman concrete, some of which has survived marine environments for nearly 2,000 years. Ancient builders often achieved durability that continues to surprise modern engineers. What do you think? Were the underground villas of Bulla Regia simply the product of experience? Or do they preserve forgotten engineering knowledge that has yet to be fully understood? Let us know your thoughts in the comments below. In the valley of northeastern Peloponnese, Greece, hidden between mountains and dry riverbeds, Sanctuary of Zeus at Nemea once hosted one of the most important athletic festivals in the ancient world. Yet beneath its ruined columns and silent stadium lies a mystery far stranger than mythology. Some of its engineering principles appear so advanced that parts of the site still function after more than 20,000 through to 100 years. The sanctuary was first systematically excavated in the late 19th century, but the most important discoveries came during major archaeological campaigns led by the University of California in the 1970s and 1980s under archaeologist Stephen G. Miller. What researchers uncovered was not just a religious complex, it was an ancient laboratory of acoustics, geometry, hydrology, and seismic engineering. The Stadium of Nemea was constructed around the 4th century BCE and could hold roughly 40,000 spectators. At first glance, it looks simple compared to Roman arenas, but beneath the track, archaeologists discovered an unusually sophisticated layered foundation system. The running surface was made from tightly compacted clay mixed with fine gravel and drainage layers beneath it. Modern soil analysis revealed that these layers distributed pressure extremely efficiently, reducing surface deformation caused by repeated impact. In simple terms, the ground behaved almost like a primitive athletic shock absorption system. This becomes even more mysterious when compared to many later Roman stadiums, whose tracks often suffered heavier erosion. Despite earthquakes, seasonal flooding, and more than 2 millennia of exposure, large portions of Nemea's track profile remain recognizable today. Some engineers comparing ancient sports surfaces estimate that the compression consistency of the Nemea track falls surprisingly close to the density management principles used in modern athletic field construction. Yet the Greeks achieved this without modern surveying equipment, industrial compactors, or geotechnical science. One of the most haunting structures at Nemea is the vaulted athlete tunnel leading directly into the stadium. The passage stretches approximately 36 meters and was built from enormous limestone blocks fitted together with remarkable precision. Inside the tunnel, sound behaves strangely. Even a whisper can echo sharply through the corridor and footsteps amplify unnaturally. Researchers studying the acoustics found that the curved stone geometry creates focused reverberation patterns similar to intentional resonance chambers. This raises a disturbing possibility. The tunnel may have been deliberately engineered to psychologically affect athletes before competition. Modern stadium architects understand how enclosed corridors can increase anticipation and emotional intensity through acoustics. But Nemea's tunnel predates most known advanced architectural acoustic theory by centuries. The effect becomes even more intriguing when compared with Greek theatres like Epidaurus, famous for near-perfect sound transmission. Some historians now believe ancient Greek builders possessed a practical understanding of resonance and wave reflection far beyond what was once assumed. The Temple of Zeus at Nemea originally stood with more than 30 massive Doric columns reaching nearly 10 meters high. Many ancient temples collapsed completely over time, especially in seismically active Greece. Yet parts of Nemea survived unusually well. The secret may lie inside the columns themselves. Each column was constructed from stacked cylindrical stone drums. Between those drums, archaeologists found metal clamps and thin lead sheets acting as flexible connectors. Instead of rigidly locking the stones together, the system allowed slight movement during seismic activity. Modern earthquake-resistant structures often use similar concepts through base isolation and controlled flexibility. The principle is simple. A structure that moves slightly during an earthquake survives better than one that resists movement completely. What shocks researchers is the sophistication of this understanding. Ancient Greek builders had no seismographs, structural simulations, or modern physics. Yet they appear to have developed empirical anti-seismic engineering through observation and experimentation. Some structural engineers studying Greek temples estimate that these flexible stone systems could dissipate small seismic vibrations surprisingly effectively compared to rigid masonry designs. Nemea sits in a region vulnerable to seasonal water flow and erosion. A poorly designed sanctuary would have been destroyed long ago. Instead, archaeologists uncovered an elaborate drainage network beneath key sections of the complex. Stone-lined channels directed rainwater away from foundations using carefully calculated slopes. Some underground conduits remain partially operational even today. This may sound ordinary until the mathematics are considered. Maintaining stable water flow across a large sanctuary requires accurate gradient control. Even a slight miscalculation causes stagnation, overflow, or erosion. Modern engineers achieve this with laser surveying and precision instruments. At Nemea, ancient builders accomplished it using basic measuring tools and geometry alone. Comparisons with other ancient hydraulic systems, including Roman aqueducts and Persian qanats, suggest the Greeks possessed an extremely advanced practical understanding of terrain mapping. The drainage gradients at parts of Nemea vary by only tiny margins over long distances, an astonishing feat for the 4th century BCE. Among all the mysteries of Nemea, none may be more unsettling than its geometric precision. Researchers studying the sanctuary noticed recurring mathematical proportions throughout the site. Distances between columns, widths of pathways, dimensions of ceremonial spaces, and alignments within the stadium appear to follow consistent harmonic relationships. Some scholars believe the builders used proportional systems related to Greek musical harmony, mathematical ratios associated with sound frequencies and balance. The idea sounds abstract until the numbers are examined. Ancient Greek mathematicians discovered that harmonious musical intervals emerge from simple numerical ratios such as 2:1, 3:2, and 4:3. At Nemea, several architectural dimensions appear to approximate these same proportional relationships. This creates a disturbing theory. The sanctuary may not have been designed purely for aesthetics. It may have been engineered according to a broader philosophy connecting mathematics, acoustics, human perception, and sacred space. The precision becomes even stranger when compared with other Greek sites like the Parthenon or Olympia. Researchers have long debated whether Greek architects intentionally embedded mathematical harmony into their structures or whether modern scholars are simply finding patterns where none exist. But at Nemea, the consistency is difficult to dismiss. Some measurements align with ratios accurate to within surprisingly small tolerances considering the technological limitations of the time. Without laser tools, digital calculations, or modern drafting systems, ancient builders somehow maintained proportional coherence across an entire sanctuary complex. This has led certain historians to propose that Greek sanctuaries functioned almost like experimental architectural cultural centres where geometry, engineering and religious symbolism merged into a single design philosophy. If true, Nemea was not merely a sports complex. It was a mathematical machine built from stone. Inside the athlete tunnel, archaeologists discovered hundreds of ancient inscriptions carved directly into the limestone walls. Some are simple names, likely athletes preparing for competition. Others are symbols and markings whose meanings remain uncertain. Several symbols repeat in patterns that do not resemble ordinary graffiti. Some researchers speculate they may have represented team identifiers, ritual symbols, or coded markings connected to initiation ceremonies. The existence of these carvings changes how historians view the Nemean Games. The competitions may not have been purely athletic events. Like many Greek festivals, they were deeply intertwined with religion, ritual purification, and symbolic performance. In that sense, the tunnel itself may have acted as a transitional chamber, psychologically transforming competitors before they entered the sacred arena. What do you think really caused the fall of Nemea? War, environmental collapse, or the loss of knowledge itself? Let us know your theory in the comments below. An enormous artificial hill rises above the medieval city of York, England, a mound first constructed by the Normans shortly after 1068. Archaeologists believe the original wooden fortress on the site was ordered by William the Conqueror during the rapid Norman occupation of northern England. After repeated fires and structural failures, the wooden keep was replaced in the 13th century by the massive stone tower that still survives today under King Henry III. Excavations across the mound revealed layers of burned timber, collapsed earthworks, medieval drainage systems, and evidence that the hill itself had been engineered with surprising sophistication. Yet the deeper researchers studied the structure, the stranger it became. Clifford's Tower was not simply another medieval fortress. Many of its engineering choices appear unusually advanced, even when compared with larger castles built centuries later. Most Norman keeps followed simple geometric designs. Castles such as the White Tower in London used square layouts because they were easier to construct and easier to reinforce, while circular towers later became common because they distributed stress more evenly and resisted siege weapons more effectively. Clifford's Tower did neither. Instead, its builders created a rare quatrefoil design, 4 overlapping circular lobes forming a clover-like structure. Very few military buildings in medieval Europe used this layout because it was far more difficult to engineer. And even today, historians debate why the designers chose such a strange shape for a defensive tower. Modern structural simulations suggest the design may have unintentionally solved several major engineering problems at once. The curved lobes distribute weight outward instead of concentrating pressure in sharp corners, reducing localized stress fractures compared with square Norman keeps. Some modern engineers comparing medieval fortifications estimate the shape could reduce impact concentration from siege projectiles by more than 20% compared with flat wall structures of similar thickness. The design also created overlapping defensive sightlines, allowing archers positioned inside the tower to observe nearly every approach angle without exposing themselves as easily as defenders in rectangular keeps. Similar principles would not become common in European military architecture until centuries later, with the star forts of the Renaissance. What makes the mystery even deeper is that medieval builders had no formal understanding of stress analysis, load transfer mathematics, or modern geometry. Yet Clifford's Tower behaves like a structure intentionally optimized for them. Some researchers believe the design may represent practical engineering knowledge accumulated through generations of builders rather than theoretical science, while others argue it may simply be a brilliant accident. Either explanation remains unsettling. The tower sits on top of a massive motte, a man-made hill composed of earth, clay, gravel, and compacted debris. Medieval records suggest the mound may originally have risen over 20 meters high, and contained tens of thousands of cubic meters of imported soil. Normally, this would be disastrous for heavy stone construction because artificial earthworks are unstable and settle unevenly over time, especially under concentrated loads. Many Norman Motte and Bailey castles across Europe eventually cracked, tilted, or collapsed entirely because their foundations shifted. Yet Clifford's Tower survived for nearly 800 years. Modern geological studies found evidence that the mound may have been built in carefully layered densities rather than as a simple pile of earth. Some sections appear intentionally compacted differently to absorb movement gradually instead of resisting it rigidly, resembling principles used in modern geotechnical engineering. Researchers also discovered traces of medieval drainage systems running through parts of the hill. Water is one of the greatest threats to earthen foundations because it changes soil density and creates internal movement. But by controlling water flow, the builders may have dramatically slowed structural failure. The mystery becomes even more remarkable when compared with other medieval sites. At locations such as Christchurch Castle and parts of Durham's early Norman fortifications, significant earth movement damaged foundations within centuries, yet Clifford's Tower remained standing through freezes, floods, fires and warfare despite its enormous weight. Some engineers believe the structure survives because the entire mound acts almost like a shock absorber, allowing tiny shifts over time rather than catastrophic cracking. The builders may have accidentally created a primitive form of flexible foundation engineering centuries before the concept formally existed. Before the stone tower existed, earlier wooden fortifications occupied the same hill. Historical records describe repeated fires, including the infamous events of 1190 connected to one of the darkest massacres in medieval English history. After these disasters, Henry III ordered the construction of a new stone fortress around 1245, but the replacement tower contains another mystery. Large portions of its stonework survived weathering far better than expected. Scientists studying the limestone found unusually durable mineral behavior compared with ordinary medieval masonry. The builders used magnesian limestone, a stone rich in magnesium carbonate. When combined with lime mortar, microscopic mineral interactions gradually formed tighter crystalline bonding over centuries. In some samples, researchers observed secondary mineralization, where dissolved compounds slowly recrystallized inside cracks, partially strengthening damaged areas naturally. In simple terms, parts of the tower may have slowly healed themselves over time. This phenomenon resembles limited self-sealing behavior observed in some Roman concrete structures exposed to seawater. While Clifford's Tower does not use Roman concrete technology, the comparison shocked researchers because both systems demonstrate unexpected long-term chemical resilience. The tower also endured extreme thermal stress. Northern England experiences constant moisture cycles, winter freezes and salt crystallization, conditions that normally destroy medieval stone rapidly. Yet portions of Clifford's Tower remained structurally stable after nearly 8 centuries. Some sections show erosion rates significantly lower than expected for exposed medieval limestone, and no one fully understands why. The interior arrangement of Clifford's Tower may have served more than military defense. Unlike straightforward rectangular keeps, the curved internal geometry creates unusual acoustics. Modern sound experiments inside the surviving chamber revealed that footsteps, voices, and metal impacts echo unpredictably across the circular lobes, meaning attackers entering the tower may have struggled to determine where defenders were positioned. The overlapping chambers also create disorienting visual movement because the walls curve continuously, causing intruders to lose their sense of direction quickly in low-light conditions filled with smoke, shouting, and combat. Military historians compare this effect to later fortress designs intentionally built to confuse attackers during close-quarter assaults. Some believe the structure functioned almost like a medieval psychological weapon. Defenders hidden behind curved corridors could sound far more numerous than they actually were. Echoes amplified movement, and blind corners increased fear. The tower's shape may have created an environment where attackers hesitated, slowed down, and became vulnerable. Whether medieval builders consciously understood these effects remains unknown, but the tower behaves as though they did. By the modern era, Clifford's Tower developed severe cracks caused by soil movement, weather expansion, and centuries of structural stress. Some fractures became large enough that engineers feared total collapse, yet the tower never failed completely. The quatrefoil geometry again appears to be the reason. In conventional square towers, stress concentrates at corners and weak points, but Clifford's curved lobes redirect pressure around the structure. When one section weakens, forces disperse into adjacent curves instead of collapsing inward immediately. Modern computer modeling suggests this design unintentionally created remarkable redundancy because damage in one area does not instantly trigger catastrophic failure across the whole tower. This principle resembles aspects of modern earthquake-resistant engineering, where structures are designed to redistribute force dynamically. For a 13th century fortress, the implications are extraordinary, especially because Europe at the time lacked mathematical tools capable of calculating such behaviours precisely. Archaeologists studying Clifford's Tower also uncovered evidence of unusually advanced internal planning. The structure included sophisticated drainage channels, elevated access systems, controlled airflow passages, large storage chambers, and latrine systems carefully positioned to reduce contamination. Ventilation appears especially advanced. Airflow studies suggest the curved internal layout naturally circulated air more efficiently than many square keeps, allowing smoke from fires to escape more effectively and reducing suffocation risks during sieges. This resembles passive ventilation concepts used in much later architecture. Some historians compare these systems to engineering solutions found in advanced Crusader fortresses or even certain Roman military structures. Yet Clifford's Tower was built in medieval northern England, not in the Mediterranean world traditionally associated with sophisticated thermal architecture. The question remains unanswered. Where did these builders learn techniques so advanced for their time? Southern Tuscany, about 8 kilometers from modern Grosseto, Italy, is home to the ruins of Rucellai, first systematically identified in the 19th century after archaeologists uncovered massive stone walls buried beneath vegetation and farmland. What initially appeared to be ordinary Etruscan ruins quickly became one of the most controversial engineering mysteries in ancient Italy. The deeper excavations went, the stranger Rucellai became. Enormous polygonal walls weighing several tons each surrounded the city for more than 3 kilometers. Underground drainage tunnels still functioned after over 2,500 years. Foundations appeared unusually resistant to seismic activity. Even Roman builders who later occupied the city reused many of the earlier Etruscan structures instead of replacing them. Today, Rucellai is often compared to ancient megalithic sites such as Sacsayhuaman, Mycenae, and Machu Picchu because of one disturbing question. How could a civilization with relatively primitive tools create structures this advanced so early in history? The most famous mystery of Rucellai is its gigantic cyclopean wall system. Some sections still stand more than 7 meters high, built from irregular limestone blocks weighing between 5 and 12 tons. Unlike later Roman walls that relied heavily on mortar and standardized bricks, Rucellai's walls were assembled through polygonal masonry, a technique where stones are cut into irregular geometric forms that lock together almost perfectly. Archaeologists measured gaps between some stones at less than 2 millimeters. Even modern masonry projects using steel tools often struggled to achieve this level of precision on irregular rock surfaces. The question is not simply how the stones were moved, but how they were shaped so accurately without advanced cutting equipment. Researchers believe the walls date primarily to the 6th century BCE, centuries before Roman engineering reached its peak. At that time, iron tools in Etruria were still relatively basic, yet many blocks at Ruscelli show unusually smooth contact surfaces, suggesting abrasion methods more sophisticated than simple hammering. Some engineers comparing Ruscelli to the walls of Sacsayhuaman in Peru noticed a similar phenomenon. Interlocking irregular stones distribute force more efficiently during earthquakes. Computer simulations conducted on polygonal masonry structures show they can absorb seismic stress significantly better than rigid rectangular block systems. In some cases, force dispersion improves by over 20% compared to conventional stacked masonry. That may explain why major sections of Ruscelli's walls survived more than 2 millennia of environmental erosion and repeated seismic activity in central Italy. One of the most controversial theories surrounding Ruscelli is that the Etruscans may have understood primitive anti-seismic engineering centuries before Roman architects documented similar principles. The walls do not follow perfectly vertical geometry. Instead, many stones are slightly angled inward, while others create pressure-locking patterns that stabilize neighboring blocks. During earthquakes, rigid walls tend to crack because energy concentrates along straight fracture lines. Polygonal systems behave differently. Stress travels across multiple irregular contact points, reducing catastrophic collapse. Modern Japanese earthquake engineering uses comparable concepts in certain interlocking foundation systems. Although the technologies are entirely different, the structural logic is surprisingly similar. What confuses archaeologists is the apparent consistency of the technique across large sections of Ruscelli. This was not random stacking. It required planning, stone selection, geometric understanding, and extremely accurate shaping. Laser analysis on several blocks revealed cut angles surprisingly consistent across different construction phases. Some researchers speculate that Etruscan builders may have used abrasive sands containing quartz crystals to polish contact surfaces. Quartz ranks 7 on the Mohs hardness scale, harder than many metals available in antiquity. When combined with water and repetitive grinding, it could theoretically produce far smoother cuts than simple chiseling alone. No direct written explanation survives from the Etruscans themselves. Their engineering methods remain largely undocumented, making Ruscelli even more mysterious. Beneath the visible ruins lies another puzzle, an underground hydraulic network designed with remarkable precision. Ruscelli was built on elevated terrain vulnerable to erosion during heavy rainfall. Normally, ancient hillside settlements suffered severe foundation instability over centuries. Yet large parts of Ruscelli remained structurally stable far longer than expected. Excavations uncovered drainage channels carved beneath streets and buildings, carefully angled to guide rainwater away from foundations. In some sections, archaeologists measured gradient variations of only a few centimeters over dozens of meters. That level of hydraulic precision is extraordinary for the ancient world. Even a small error in slope would have caused stagnation or destructive overflow. The Romans later became famous for aqueducts and water management systems, but many historians believe they inherited substantial engineering knowledge from the Etruscans. Ruscelli may represent one of the earliest large-scale experiments in urban hydraulic control in Italy. Some channels still drain water effectively today after more than 20,500 years underground. Another mystery involves the unusual preservation of Ruscelli's masonry. Limestone normally degrades significantly under long-term exposure to rain, temperature shifts, and biological growth. Tuscany's climate includes moisture fluctuations capable of accelerating stone decay. Yet portions of Ruscelli's walls remain structurally intact despite over 2 millennia of weather exposure. Some researchers believe the answer lies partly in the precision of the masonry itself. Tight-fitting stones reduce water infiltration, preventing freeze-thaw cracking that destroys many ancient walls. Others suggest the builders deliberately selected unusually dense limestone with low porosity. Microscopic analysis of some surfaces also revealed signs of repeated polishing or finishing that may have reduced weather penetration. Similar preservation mysteries appear at sites like Alatri and Delphi, where polygonal walls survived far better than nearby conventional masonry. The durability becomes even stranger when compared to many medieval structures in the same region that deteriorated much faster despite being built over 1,000 years later. Rucellai later developed into a Roman city, and one of its most famous surviving structures is the theatre constructed partly atop older Etruscan foundations. Acoustic studies conducted in ancient theatres across the Mediterranean repeatedly show unexpectedly advanced sound engineering. Rucellai is no exception. Even with partial claps, voices spoken at normal volume near the stage remain audible from upper seating areas. Researchers studying classical acoustics discovered that the curved seating geometry and limestone surfaces naturally amplify certain speech frequencies between roughly 500 and 2000 Hz, precisely the range most important for human vocal clarity. The slope angle of the theatre also appears carefully optimized. If the incline were too shallow, sound would dissipate. Too steep, and echoes would distort speech intelligibility. Modern theatres often require digital acoustic modelling to achieve similar clarity. Yet ancient engineers managed it using only geometry and material behaviour. Whether this knowledge came from empirical experimentation or deeper mathematical understanding remains unknown. Perhaps the strangest aspect of Rucellai is that Roman builders reused large portions of the earlier Etruscan city rather than demolishing it completely. The Romans were famous for rebuilding conquered cities according to their own urban standards. Yet at Rucellai, they incorporated existing foundations, roads, and defensive structures into later construction phases. This suggests the earlier engineering was already considered highly reliable. Archaeological surveys indicate that some Roman structures were positioned specifically to exploit the stability of older Etruscan foundations. In several locations, Roman walls directly connect into much older polygonal masonry because replacing it would have been less practical than reusing it. That creates a disturbing possibility. Parts of Rucellai's engineering may have surpassed what later Roman builders could easily replicate. Do you think the builders of Rucellai discovered engineering principles that were lost for thousands of years? Share your theory in the comments below. Western Armenia's Arashrat Plain near the banks of the Aras River hides the ruins of Argishti Kinili, an Iron Age city built nearly 2,800 years ago. Beneath its collapsed walls lies evidence of engineering, metallurgy, and logistical capabilities that researchers still struggle to fully explain. Argishti Kinili was first identified through archaeological investigations during the 20th century after inscriptions of King Argishti had revealed the existence of a major Eurasian administrative centre. Excavations uncovered fortifications, granaries, irrigation systems, workshops, and thousands of artifacts that transformed the understanding of the ancient kingdom of Urartu. One of the first mysteries surrounding Argishti Kinili is the speed at which it seems to have emerged. Historical inscriptions suggest that the city was founded during the reign of Argishti I, around 776 BCE. Unlike settlements that evolved gradually over centuries, Argishti Kinili appears to have been planned from the beginning. Archaeological surveys reveal organized districts, defensive structures, storage facilities, administrative areas, and industrial zones integrated into a coherent urban plan. This immediately raises questions because planning a city requires accurate knowledge of terrain, water supply, transportation routes, population requirements, and military strategy. Modern urban planners rely on satellite imagery, topographic surveys, and digital modelling software, yet the builders of Argishti Kinili possessed none of these tools. Even so, the city functioned as a highly organized administrative machine, and researchers continue debating how Eurasian engineers measured, mapped, and coordinated such large-scale construction projects with remarkable precision. Perhaps the most visible technological achievement of Urartu was water management. The Ararat Plain experiences hot summers and relatively limited rainfall, making large-scale agriculture dependent on artificial irrigation. Excavations throughout former Eurasian territory have revealed canals extending for dozens of kilometers, and some channels maintained gradients so precise that water could flow efficiently across long distances without causing erosion or stagnation. Even today, irrigation engineers understand that extremely small errors in slope calculations can cause major failures. A canal descending too rapidly destroys its own banks, while a canal descending too slowly may stop flowing altogether. The challenge becomes even greater over distances exceeding 20 or 30 kilometers. Ogishtikinili depended on this hydraulic infrastructure, and the mystery is not whether the canals worked, because archaeological evidence proves they did. The real mystery is how surveyors achieved such accuracy without modern instruments. Some scholars compare Eurasian hydraulic achievements to the Roman aqueducts that would appear centuries later, while others suggest that the kingdom developed surveying techniques that were largely lost after its collapse. Of all the technological puzzles associated with Ogishtikinili, none may be more fascinating than metallurgy. The kingdom of Urartu was famous throughout the ancient Near East for its metalworking, and Assyrian records frequently described Eurasian wealth in terms of metals, weapons, armor, and crafted objects. Archaeological excavations have uncovered iron tools, bronze artifacts, weapons, slag deposits, furnace remains, and evidence of large-scale metal production. At first glance, ancient metallurgy may seem simple. In reality, it represents one of the most difficult technological challenges ever mastered by early civilizations. Producing useful iron requires temperatures approaching 1,200 degrees Celsius or higher, and maintaining such temperatures demands precise control of airflow, fuel quality, furnace design, and ore composition. A furnace that receives too little oxygen cannot reach sufficient temperatures, while a furnace that receives too much oxygen may consume fuel inefficiently or damage the metal being produced. The astonishing fact is that Eurasian metalworkers achieved consistency. Thousands of artifacts recovered from Eurasian sites demonstrate standardized production methods rather than occasional experimentation, suggesting generations of accumulated technical knowledge. Yet almost none of that knowledge survives. No Eurasian metallurgical manuals have been discovered, no engineering texts explain furnace construction, and no technical diagrams reveal how airflow was regulated. Modern experimental archaeologists attempting to recreate ancient iron production often discover that seemingly simple furnaces hide extraordinarily complex engineering principles. Airflow patterns inside a furnace can determine whether iron forms successfully or fails entirely, and even minor differences in furnace geometry can dramatically affect efficiency. Researchers studying ancient slag have found evidence that some Iron Age metallurgists understood these relationships remarkably well despite lacking modern chemistry. The mystery becomes even greater when bronze production is considered. Bronze requires carefully controlled ratios of copper and tin, and both materials often originated from different locations. This means Eurasian craftsmen not only mastered metallurgy, but also maintained supply networks capable of delivering essential raw materials over significant distances. Comparisons with other ancient civilizations make the puzzle even more intriguing. The famous ironworking traditions of the Hittites remain partially understood. The metallurgical achievements of ancient Africa continue surprising researchers today, and Roman metallurgy reached industrial scales that were once thought impossible for the ancient world. Urartu belongs within this same category of technological excellence. The difference is that far less documentation survives. As a result, historians can see the product but not the complete process. The machines vanished, the engineers vanished, and only the results remain. Argishtikinili also demonstrates remarkable defensive engineering. The city occupied strategically advantageous terrain overlooking critical transportation routes, and its walls were designed not merely as barriers but as integrated military systems. Construction required moving enormous quantities of stone and earth. Without cranes, engines, or mechanized transportation, laborers somehow assembled fortifications capable of surviving for millennia. Many ancient defensive structures eventually collapsed entirely, yet portions of Argishtikinili's foundations remain recognizable after nearly 28 centuries. This durability suggests a sophisticated understanding of structural stability, load distribution, and construction techniques. How much of this knowledge was based on formal engineering principles and how much derived from experience remains uncertain. Excavations uncovered massive storage facilities capable of holding huge quantities of grain. These installations were essential for supporting armies, administrators, craftsmen, and local populations. Ancient grain storage was far more complicated than simply filling containers, as moisture, insects, fungi, rodents, and temperature fluctuations constantly threatened supplies. Even modern storage facilities require careful environmental management. Yet many ancient societies successfully preserved food for extended periods. Argishtikinili appears to have operated on a scale suggesting advanced logistical planning, and researchers continue investigating how airflow, architecture, and storage design may have helped protect vital resources. Perhaps the greatest mystery of Argishtikinili is the knowledge that no longer exists. Before constructing canals, walls, roads, workshops, and administrative buildings, engineers needed accurate measurements. They needed to understand gradients, calculate distances, and align structures across complex terrain. Today, such work depends on laser scanners, GPS receivers, drones, and digital mapping systems. The builders of Argishtikinili possessed none of these technologies, yet the archaeological record demonstrates results that required impressive precision. Central Germany contains one of the strangest Celtic sites ever discovered. Beneath the grassy earthworks of Glauberg lies a place where Iron Age engineering, astronomical alignment, elite burials, and stone-carving technology appear far more advanced than historians once believed possible. The site was rediscovered through aerial photography and later geophysical scans during the late 20th century. What initially looked like ordinary farmland revealed enormous circular ditches, buried walls, processional pathways, and massive tomb structures hidden beneath the soil for more than 20,400 years. Archaeologists soon realized Glauberg was not simply a burial mound. It was an enormous ceremonial and political complex, built with mathematical precision during the 5th century BCE. But the greatest mystery at Glauberg emerged in 1996. Inside one of the burial mounds, archaeologists uncovered the grave of an elite Celtic ruler now known as the Prince of Glauberg. The burial contained weapons, jewelry, imported goods, and one of the most extraordinary discoveries ever made in Celtic archaeology. A life-size sandstone statue standing nearly 1.9 meters tall. The statue immediately shocked researchers because nothing like it was supposed to exist in the Celtic world of that period. Unlike the rough symbolic carvings associated with many Iron Age cultures, the Prince of Glauberg displayed astonishing technical sophistication. The proportions of the body were balanced with unusual precision. The curvature of the torque necklace showed nearly symmetrical shaping. The facial structure, armor details, and famous leaf-shaped headdress demonstrated advanced stoneworking methods that many experts believed Celtic artisans had not yet mastered. Microscopic analysis later revealed evidence of controlled chiseling techniques using multiple grades of iron tools. Certain grooves appear to have been polished repeatedly with abrasive materials, possibly quartz-rich sand or fine mineral powders. As experimental archaeologists attempting to recreate the carving found that producing similar surface smoothness with Iron Age tools would require extraordinary craftsmanship and patience. The headdress itself remains one of the greatest mysteries. The strange curved projections resemble mistletoe leaves or lunar horns, but no definitive explanation exists. Some researchers believe it symbolized royal authority linked to celestial cycles. Others think it may represent ritual attire used in seasonal ceremonies. The precision of the carving suggests the sculptor was following a standardized symbolic system, rather than improvising decorative art. Even more puzzling is the Mediterranean influence visible in the statue. Several anatomical proportions resemble sculptural conventions seen in Greek Kouros statues from roughly the same era. Imported artifacts found inside the tomb, including Mediterranean drinking vessels, prove long-distance trade connections existed between Celtic elites and southern Europe. This has led some historians to propose that Glauberg may have been part of a much larger exchange network connecting Celtic Europe to Greek and Etruscan civilizations. If true, then the traditional image of isolated barbarian tribes collapses completely. One of the first mysteries surrounding Glauberg is its scale. The fortified hilltop enclosure stretches across nearly 20 hectares, protected by earthworks and wooden defensive walls that would have required tens of thousands of labor hours to construct. Soil analysis revealed carefully layered engineering techniques involving compacted clay, gravel, and timber reinforcements designed to prevent erosion. Even after more than 2 millennia of rain, frost, and agricultural activity, large sections remain intact. This immediately created a problem for historians. Celtic societies of this period were traditionally portrayed as loosely organized tribal cultures lacking centralized engineering systems. Yet Glauberg suggests the opposite. The coordination required to reshape entire hillsides, transport timber, excavate deep ditches, and maintained geometric layouts indicates an advanced political structure capable of organizing hundreds, possibly thousands of workers. What makes the site even stranger is its apparent astronomical alignment. Archaeological surveys found that several ditches and processional avenues appear oriented toward the winter solstice sunrise. Similar alignments are seen at places like Stonehenge and Newgrange. But Glauberg dates to a later Iron Age Celtic culture not usually associated with monumental sky-based architecture. Researchers discovered that one major avenue leading toward the burial mound deviates only slightly from the solar rising point during the winter solstice at that latitude. Such precision would require long-term astronomical observation across generations. The question is how Iron Age builders achieved this accuracy without advanced optical tools. Some archaeologists believe they used shadow tracking systems involving wooden poles and seasonal horizon markers. Others argue the alignments may have held symbolic rather than scientific meaning. Either way, the geometry was intentional. The prince's tomb also contained gold ornaments manufactured with remarkable metallurgical precision. Spectroscopic studies on the torque and jewelry revealed highly controlled alloy compositions with surprisingly low impurity levels. The twisted gold neck rings display almost perfectly consistent rotational symmetry, suggesting skilled temperature management during metalworking. Some metallurgists compared the uniformity to techniques used centuries later by Roman craftsmen. Another unexplained feature is the burial mound itself. Ground-penetrating radar showed the mound was constructed in multiple engineered phases. Builders layered clay, stones, organic material, and compacted soil in ways that distributed weight evenly across the structure. Modern geoarchaeologists noted similarities between the mound stabilization techniques and later Roman embankment engineering. Yet Glauberg predates major Roman expansion into the region by several centuries. Excavations around the mound also uncovered enormous wooden post alignments extending hundreds of meters across the landscape. These timber avenues may have functioned as ceremonial corridors or astronomical sightlines. Some post holes were over 1 meter wide, indicating the use of massive tree trunks likely transported from distant forests. The logistics behind this operation remain difficult to explain. Cutting, transporting, shaping, and erecting such timber structures without advanced machinery would require sophisticated planning and workforce coordination. Some estimates suggest hundreds of people may have participated in construction projects lasting decades. There is also evidence that Glauberg functioned as both a ritual center and a political stronghold. Archaeologists discovered imported luxury goods, high-status weaponry, feasting equipment, and elite burial practices concentrated around the central mound. This indicates the site may have served as the residence of a regional ruler controlling trade routes through Central Europe. Its strategic position supports this theory. Glauberg overlooked important movement corridors connecting northern and southern Europe. Control of these routes would have provided access to metals, salt, amber, wine, and Mediterranean imports. But perhaps the most disturbing mystery is how completely the site vanished from memory. Unlike Roman settlements, Glauberg left behind no written records explaining its builders, rulers, rituals, or collapse. By the time later civilizations expanded across the region, the ceremonial complex had already faded into silence beneath the earth. No surviving Celtic text describes the prints, the mound, or the enormous astronomical earthwork surrounding it. For centuries, the landscape appeared ordinary. Only modern remote sensing technologies exposed the hidden geometry buried below the fields. Magnetometry surveys revealed invisible ditches. LiDAR scans uncovered ancient alignments impossible to detect from ground level. What seemed like natural hills turned out to be engineered monuments, created with deliberate mathematical planning. Do you think the people of Glauberg possessed knowledge far beyond what historians expected from the Iron Age? Or are we only beginning to understand how advanced the ancient Celtic world truly was? Share your thoughts in the comments below. Clunia was discovered across the windswept plateau of northern Spain, nearly 1,000 meters above sea level, where Roman ruins emerged from layers of limestone and buried tunnels. Archaeologists first began serious excavations in the early 20th century after scattered inscriptions, collapsed galleries, and enormous carved stone structures were identified beneath farmland near Burgos. What they uncovered shocked historians. Clunia was not a small provincial settlement. At its peak during the 1st and 2nd centuries AD, the city may have supported more than 30,000 inhabitants, making it one of the largest Roman urban centers in Hispania. Yet the region surrounding it had limited natural water sources, harsh winters, and unstable rocky terrain. The existence of a massive city here immediately raised a question that still has no complete answer. How did Roman engineers sustain a metropolis of this scale in such an unforgiving location? The greatest mystery of Clunia lies beneath the surface. Hidden under the city is a gigantic hydraulic network carved directly into limestone bedrock. Massive cisterns, underground reservoirs, drainage shafts, and water tunnels stretch for kilometers beneath the plateau. Modern surveys show that some channels maintain gradients accurate to only a few millimeters per meter, precise enough to keep water flowing continuously without damaging the walls through erosion. For comparison, maintaining stable water gradients is one of the most difficult challenges in pre-industrial engineering. Even slight miscalculations can cause stagnation or destructive flooding. Roman aqueducts like those at Pont du Gard achieved average slopes of around 34 centimeters per kilometer. Some tunnels beneath Clunia appear comparably precise despite being cut through solid underground rock with limited visibility. Researchers remain divided over how Roman surveyors achieved this level of accuracy. Traditional explanations involve water levels, plumb lines, and manual geometry. However, some archaeologists argue that the complexity of Clunia's underground design suggests generations of accumulated engineering knowledge far beyond what most ancient provincial cities should have possessed. Even more mysterious is the city's water storage capacity. Estimates suggest the underground reservoirs could store millions of litres of water simultaneously. In a region vulnerable to seasonal drought, Clunia may have functioned almost like a self-contained survival system capable of resisting long-term sieges or climate instability. Clunia was built atop naturally fractured limestone filled with caves and cavities, but Roman engineers appear to have expanded these spaces into an enormous artificial underground complex. Excavations revealed carved chambers with ventilation shafts, storage areas, hidden corridors, and carefully smoothed ceilings designed to reduce structural collapse. What fascinates modern engineers is the climate stability underground. Temperature readings inside some chambers remain relatively constant throughout the year despite extreme seasonal differences outside. Humidity levels are also surprisingly controlled. This has led researchers to compare Clunia's underground spaces to passive cooling systems found in ancient Persian architecture, particularly the wind-catching ventilation systems used in desert cities thousands of kilometers away. Some theories suggest the underground galleries acted as a thermal regulator for buildings above the surface. Cool air circulating through lower tunnels may have naturally reduced heat during summer while stabilizing temperatures during winter. If true, Clunia may represent one of the earliest large-scale examples of environmental engineering in Roman Europe. Ground-penetrating radar studies indicate that much of this subterranean system still remains unexplored. Several anomalies detected beneath the known ruins suggest the existence of deeper chambers that archaeologists have not yet entered. Among the most astonishing structures at Clunia is its enormous Roman theatre, carved directly into the hillside. The theatre could seat approximately 10,000 spectators, making it one of the largest in Roman Spain. But its true mystery is not its size, it is its sound. Modern acoustic measurements show that voices projected from the central stage can still be heard clearly from the upper seating levels without electronic amplification. Researchers studying Roman theatres have long known that curved seating improves sound reflection, yet Clunia appears unusually efficient even compared with famous theatres such as Theatre of Epidaurus. Acoustic engineers believe the limestone composition itself may have contributed to sound filtering. Certain frequencies are naturally absorbed while human speech frequencies are reflected upward through the seating structure. Some studies suggest Roman architects intentionally manipulated angles and stone geometry to maximize vocal clarity. The mystery becomes deeper because no surviving Roman text explains these acoustic techniques in detail. Vitruvius described general architectural principles, but Clunia's theatre performs with a precision that many researchers believe required extensive real-world experimentation rather than simple theoretical knowledge. Another unexplained feature of Clunia involves the durability of its construction materials. The plateau experiences freezing winters, strong winds, and severe seasonal erosion. Over nearly 2,000 years, large portions of walls, drainage systems, and foundations have survived far better than many younger medieval structures nearby. Chemical analysis reveals that Roman builders used mortar mixtures containing lime, volcanic ash, and reactive minerals capable of continuing chemical bonding long after construction. Similar reactions have been identified in Roman marine concrete from ports across the Mediterranean, where mineral growth actually strengthens structures over time. The mystery is geographical. Clunia lies far from major volcanic regions. Transporting large quantities of volcanic material across Roman Spain would have required a sophisticated logistical network involving roads, carts, labourers, and supply coordination on a massive scale. Some researchers estimate that certain Roman construction projects moved thousands of tons of material across hundreds of kilometers. This level of infrastructure management resembles the organizational complexity of early industrial states, more than what many people associate with the ancient world. Several streets and ceremonial structures inside Clunia do not align naturally with the terrain. Instead, their orientation appears connected to solar movement during specific times of the year. During summer solstice sunrise, light can pass through particular corridors and illuminate parts of the city with remarkable precision. This phenomenon has led archaeologists to compare Clunia with sites such as Chaco Canyon and Machu Picchu, where architecture appears intentionally synchronized with celestial cycles. Some historians argue these alignments were symbolic rather than scientific. Others believe Roman engineers integrated astronomy directly into urban planning to reinforce imperial ideology, religious ritual, or seasonal timekeeping. Satellite analysis has also revealed geometric relationships between roads, gates, and elevated structures that may indicate long-distance surveying methods. Achieving such alignment without modern instruments remains one of the enduring puzzles of ancient engineering. Despite more than a century of excavation, large sections of Clunia remain buried. Modern radar scanning has identified rectangular anomalies, deep corridors, and enclosed voids beneath areas that have never been opened. Some underground chambers appear unusually large compared to ordinary Roman storage facilities. Their purpose remains unknown. Speculation ranges from hidden archives and ceremonial chambers to emergency shelters or military infrastructure. What makes Clunia especially mysterious is the absence of detailed written explanations. Roman records mention the city politically, but almost nothing survives describing the advanced underground engineering beneath it. In other words, one of the most technologically sophisticated Roman cities may have left behind almost no surviving technical documentation. That absence creates a disturbing possibility. Some Roman engineering knowledge may have been practical, local, and transmitted directly between specialists rather than systematically recorded. Do you think Clunia was simply an advanced Roman city, or evidence that some ancient engineering knowledge has been completely lost to history? Share your thoughts in the comments below. More than 130 meters above sea level in the mountains of Arcadia, Greece stands a temple that should not exist. Hidden deep within the rocky wilderness of the Peloponnese, Bassae survived earthquakes, violent weather, isolation, and more than 2,400 years of erosion. Yet the greatest mystery is not its survival. It is the fact that this remote structure appears to contain architectural ideas centuries ahead of its own civilization. The Temple of Apollo Epicurus at Bassae was rediscovered in 1765 by the French architect Joachim Bocher while he was traveling through the mountains. At the time, much of the structure was buried beneath collapsed stone and debris. Early excavations in the 19th century revealed something astonishing. Inside this lonely mountain temple stood what many historians now consider the oldest known Corinthian column ever built. That discovery changed the history of Greek architecture. The single Corinthian column inside Bassae remains one of the most controversial architectural anomalies in the ancient world. Most historians associate Corinthian architecture with the later Hellenistic and Roman eras, especially massive Roman temples built centuries after Bassae. Yet this column was constructed around 420 to 400 BCE, possibly designed by Iktinos, the same architect connected to the Parthenon in Athens. The problem is timing. At Bassae, the Corinthian style appeared nearly 150 years before it became common across the Mediterranean. Its carved acanthus leaves are so symmetrical and geometrically refined that some researchers argue the stoneworkers must have used advanced proportional systems rarely documented in surviving Greek texts. Modern laser analysis of Greek architectural fragments has shown that master builders often achieve tolerances within only a few millimeters, despite working entirely by hand. At Bassae, the precision becomes even more mysterious because the temple stands in an isolated mountain region far from major urban workshops. Some archaeologists compare this leap in architectural experimentation to discovering Renaissance engineering hidden inside a medieval fortress. Even stranger, the Corinthian column was placed inside the temple rather than outside where it could be publicly admired. This suggests the column may have carried ritual or symbolic significance beyond decoration. Some theories propose it represented Apollo himself, acting as a sacred axis between heaven and earth. No written explanation from the builders survives. Bassae sits in one of the most seismically active regions in Greece. The Peloponnese has experienced destructive earthquakes for thousands of years, yet much of the temple remained standing long after many surrounding structures collapsed. Modern structural studies revealed something unusual in the way Bassae was assembled. Unlike rigid stone systems used in many Greek temples, parts of Bassae appear designed to absorb stress rather than resist it directly. Certain stone joints allow microscopic movement during seismic vibrations. This resembles principles found in some modern earthquake-resistant structures. Researchers studying ancient anti-seismic engineering often compare Bassae with later Roman techniques or even Japanese wooden pagodas that survive earthquakes through controlled flexibility. At Bassae, some limestone blocks were connected using iron clamps and carefully calculated spacing that distributed pressure across the structure. The temple's location makes the mystery even greater. Transporting thousands of tons of limestone up steep mountain terrain would already have been an extraordinary logistical achievement. Designing it to survive earthquakes at the same time suggests an engineering awareness far beyond what many historians once assumed about classical Greece. Most Greek temples face east. Bassae does not. Instead, the temple follows an unusual north-south orientation that continues to confuse archaeologists today. This design may have allowed sunlight to enter the temple interior at specific seasonal moments connected to Apollo, the god of light. Some researchers believe the side doorway of the temple was positioned to channel the first rays of the summer sunrise directly toward the sacred interior chamber. Simulations using astronomical software suggest the lighting effects would have been dramatic, especially during certain days of the year. This has led to comparisons with solar alignments seen in places like Newgrange or Abu Simbel, where ancient builders manipulated sunlight with astonishing precision. But Bassae presents an additional challenge. The temple was built on rugged, mountainous terrain, where horizon lines constantly shift because of surrounding peaks. Achieving accurate solar alignment under those conditions would have required careful long-term observation. Some historians believe the builders may have tracked solar movement across the mountains for years before construction began. The climate around Bassae is brutal. Winters bring freezing temperatures and mountain storms, while summers become dry and intensely hot. Yet evidence suggests the temple may have incorporated passive climate control principles rarely associated with Greek architecture. The arrangement of columns and openings appears to create natural airflow channels through the interior. Wind moving down from the mountains could circulate through the structure, reducing heat buildup during summer months. Modern engineers studying passive cooling systems often compare this concept to Middle Eastern wind towers developed many centuries later. The orientation of the temple may also have minimized direct sunlight exposure during the hottest parts of the day, while still allowing ritual illumination at carefully chosen moments. Combined with thick limestone walls capable of storing thermal energy, Bassae may have functioned as a naturally regulated environment. This is particularly surprising because surviving Greek texts contain little direct discussion of airflow engineering on this scale. One of the greatest unanswered questions is how Bassae was built at all. The temple stands far from major cities, quarries, and ancient transport routes. Even today, Reaching the site requires travelling through winding mountain roads, yet ancient workers somehow transported multi-ton stone blocks, carved architectural elements, and iron reinforcements into this isolated environment over 2,400 years ago. Researchers estimate some blocks weighed several tons each. Without cranes, engines, or modern roads, construction would have required massive coordinated labour forces using ropes, sledges, wooden rollers, and inclined ramps. The problem is geography. The steep slopes around Basaya make large-scale transport operations incredibly difficult. Some historians argue seasonal construction schedules may have been necessary, with materials moved only during certain weather conditions. Others believe the builders developed temporary mountain infrastructure that disappeared long ago. Comparisons are often made with the transportation mysteries surrounding the stones of Stonehenge or the high-altitude construction of Machu Picchu. But Basay remains unique because it combined remote logistics with extremely refined architectural precision. Excavations at Basay uncovered one of the most remarkable sculptural friezes in ancient Greece. The marble panels depicted battles between Greeks, Amazons, and centaurs with unusually dynamic movement and emotional intensity. Some art historians argue the Basay frieze anticipated stylistic developments that became common only generations later. The carvings demonstrated advanced understanding of anatomy, motion, and perspective. Muscles twist naturally, bodies overlap realistically. Faces display emotional variation rarely seen in earlier classical sculpture. Several experts describe the artistic leap at Basay as strangely isolated, almost as if experimental techniques were tested there before spreading across Greece. Today, many of the original sculptures are housed in the British Museum, where ongoing analysis continues to reveal microscopic traces of pigments once used to colour the stone. That discovery shattered the old belief that Greek temples were entirely white. Do you think the builders of Basay possessed engineering knowledge far beyond what history officially recognises? Share your thoughts and theories in the comments below. Mactaras is one of the most overlooked archaeological mysteries in North Africa. Located in modern-day northwestern Tunisia, approximately 140 kilometers southwest of Tunis and nearly 900 meters above sea level, the ancient city sits on a rocky plateau where water is limited. Winters can be harsh, and construction conditions are far from ideal. Yet, for centuries, Mactaras flourished as a major urban centre. Today, its ruins reveal evidence of sophisticated engineering, urban planning, hydraulic technology, and construction techniques that continue to raise questions among archaeologists and historians. Unlike the Great Pyramid of Giza, which is famous for a single monumental achievement, Mactaras presents a different mystery. The entire city appears to have functioned as a complex technological system. Roads, reservoirs, public buildings, temples, workshops, and residential districts work together in a way that suggests advanced practical knowledge. The problem is that very little documentation survives to explain how this knowledge was acquired, transmitted, or applied. The site was first documented by European explorers and scholars during the 19th century. Systematic archaeological investigations throughout the 20th century gradually revealed a city whose history stretched from the Numidian period into the Roman era. Excavations uncovered temples, baths, forums, triumphal structures, water installations, and one of the most remarkable monuments in North Africa, the Scola Juvenum, a large building associated with a youth organisation that still preserves inscriptions and architectural details. Yet, despite more than a century of research, many aspects of the city's engineering remain only partially understood. The first major mystery concerns water. Mactaras was built on elevated terrain without access to a major river. Modern cities facing similar conditions depend on pumps, reservoirs, treatment plants, and computerized management systems. Ancient Mactaris had none of these advantages. Nevertheless, archaeological evidence reveals an extensive network of cisterns, channels, collection systems, and storage facilities capable of supporting thousands of residents. Researchers estimate that public baths alone could consume tens of thousands of litres of water every day. Roman baths elsewhere in the empire often required between 20,000 and 100,000 litres daily depending on size. Maintaining such facilities on a high plateau required careful planning. Rainwater harvesting appears to have played a major role, but many details remain uncertain. How were storage capacities calculated? How did engineers predict seasonal shortages? How were losses from evaporation minimized? Some reservoirs survived for nearly 2 millennia, suggesting a level of hydraulic expertise that rivals many pre-industrial societies. The challenge becomes even more impressive when compared to other ancient hydraulic systems. Petra in modern Jordan developed complex water channels to survive in the desert. Roman aqueducts transported water across hundreds of kilometers. The Nabateans mastered water conservation in arid environments. Mactaris belongs within this tradition, yet unlike Petra or Rome, it lacked a large-scale aqueduct network supplying a constant flow of water. Its survival depended on managing limited resources with extraordinary efficiency. The second mystery involves stoneworking and construction. Throughout the site, enormous stone blocks were cut, transported, and assembled with remarkable precision. Some structures remained standing despite centuries of earthquakes, erosion, and human activity. Modern engineers studying ancient construction often emphasize the logistical challenges rather than the cutting itself. A stone block weighing 10 or 20 tons is not impossible to carve. The real challenge is moving it across uneven terrain without cranes, trucks, hydraulic lifts, or modern machinery. Experimental archaeology has demonstrated that ancient workers could move heavy stones using ropes, sledges, rollers, and manpower. However, scaling such methods to the level observed at Mactaris raises difficult questions. Large public buildings required hundreds or even thousands of tons of stone. Quarries supplied material over extended periods. Transport routes had to remain functional. Construction schedules had to be coordinated. The city effectively operated a long-term industrial system centuries before the Industrial Revolution. This leads directly to another mystery: organization. Modern infrastructure projects rely on managers, engineers, logistics specialists, architects, surveyors, accountants, and supply chains. Mactaris clearly required similar functions, yet little evidence survives regarding how such operations were administered. No engineering manuals have been discovered. No construction blueprints survive. No detailed descriptions explain how labor was coordinated. The city itself proves the system existed, but the mechanisms behind it remain largely invisible. One of the most intriguing questions involves surveying technology. Before construction could begin, builders needed accurate measurements. Roads had to align with public spaces. Buildings required stable foundations. Drainage systems depended on carefully controlled gradients. Today, such tasks are performed using GPS receivers, laser scanners, drones, satellite imagery, and digital modeling software. Ancient surveyors relied on simple instruments, geometry, and observation, yet the results often display surprising precision. Across the Roman world, engineers regularly achieved alignments accurate to within fractions of a degree. Similar achievements can be seen in Roman roads, aqueducts, and military camps. Mactaris demonstrates the same pattern. The city appears carefully planned despite being built on irregular terrain. How ancient surveyors achieved this consistency remains a subject of ongoing study. Another mystery concerns material science. Many structures at Mactaris survived nearly 2,000 years of environmental exposure. Temperature fluctuations, seasonal rainfall, wind erosion, biological growth, and human activity normally destroy ancient buildings over long periods. Yet substantial portions of the city remain recognizable. The durability of ancient construction materials continues to surprise researchers worldwide. Roman concrete, for example, has survived marine environments for nearly 2,000 years and remains the subject of scientific investigation. Studies have shown that certain Roman concretes developed self-healing properties through chemical reactions involving limeclasts. Similar questions arise at Mactaris. What mortars were used? How were they formulated? Did local craftsmen possess specialized knowledge of aggregates, binders, and stone selection that has since been lost? The answer may never be fully known because ancient builders rarely documented their methods in ways that survived. Archaeologists can analyze chemical compositions, microscopic structures, and construction techniques, but reconstructing the complete technological process remains difficult. Perhaps the most fascinating mystery is the relationship between Numidian and Roman engineering. Mactaris existed before becoming fully integrated into the Roman world. The city developed within a region influenced by indigenous North African traditions long before Roman administration arrived. As a result, archaeologists continue debating which technological achievements originated locally and which were introduced from elsewhere. This question has broader implications. Traditional historical narratives often portray advanced engineering as something that flowed outward from major imperial centers. However, evidence from North Africa increasingly suggests a more complex reality. Indigenous societies possess their own expertise in construction, water management, agriculture, and urban organization. Mactaris may represent a fusion of Numidian and Roman knowledge rather than a simple transfer of technology in one direction. Southern France once hid an Iron Age fortress between Narbonne and Béziers that watched over Mediterranean trade routes for more than 20,500 years. But the greatest mystery was never the walls or the weapons, it was water. Around the hill lies one of the strangest hydraulic landscapes in Europe, including the enormous radial drainage system of Montady, a gigantic wheel carved into the earth so precise that modern engineers still debate how ancient builders calculated it without advanced instruments. The ruins of UnSolved became widely recognized during the 19th century after excavations uncovered houses, storage pits, defensive walls, imported Greek amphorae, and underground cisterns. Archaeologists soon realized the settlement was not an isolated tribal fortress. It was a major urban center occupied from roughly the 6th century BCE to the 1st century CE. Excavations revealed evidence of Mediterranean trade on a surprisingly large scale. Thousands of wine amphora fragments from Greece, Massalia, and later Rome were discovered on the hill. This suggested a wealthy population living in a region with severe seasonal droughts. That contradiction became one of the site's greatest enigmas. How could a dense Iron Age city survive for centuries on a dry limestone plateau with limited natural water? The answer appeared to involve engineering far more advanced than historians once believed possible for Celtic Iberian societies. The most controversial mystery surrounding UnSolved lies only a few kilometers away: the circular drainage system of Montady. Seen from the air, the landscape resembles a colossal wheel nearly 1.3 kilometers wide. Long radial canals extend outward from a central basin like spokes on a bicycle wheel. Every channel slopes with extraordinary precision toward a drainage tunnel that removes water from the marshland. Most historians officially date the current system to the 13th century. However, many researchers suspect the medieval engineers may have inherited older surveying knowledge connected to the people of UnSolved. The reason is simple. The geometry is astonishingly accurate. To drain marshlands successfully, every canal required a carefully controlled hydraulic gradient. Even a vertical error of only a few centimeters across hundreds of meters could cause standing water, erosion, or catastrophic flooding. Yet the canals maintain remarkable consistency despite being constructed centuries before laser surveying equipment. Modern hydraulic engineers studying similar systems explain that maintaining water flow across flat terrain requires precise gravitational calculations. Ancient builders would have needed methods to measure elevation differences smaller than the width of a human hand over enormous distances. Some theories suggest they used reflective water basins, solar alignments, or primitive leveling instruments based on floating markers. Others believe generations of empirical observation allow them to understand terrain gradients with surprising sophistication. The drainage tunnel itself adds another mystery. Water from the radial channels was directed through a long underground conduit toward lower terrain beyond the hill. Excavations show the tunnel maintained stable flow despite seasonal storms common to Mediterranean climates. Engineers today still use nearly identical principles in agricultural drainage systems. The scale alone is staggering. The circular field covers roughly 420 hectares. For comparison, many Iron Age European settlements occupied less than 20 hectares total. This raises an uncomfortable possibility for historians. Either medieval builders independently rediscovered highly sophisticated hydraulic engineering, or knowledge from much older civilizations survived far longer than previously believed. Another mystery involves the water storage technology inside UnSolved itself. Archaeologists uncovered cisterns coated with an unusually durable waterproof plaster. Some sections remained intact after more than 2 millennia despite heat, erosion, and mineral exposure. Chemical analysis suggests mixtures of lime, crushed ceramics, sand, and volcanic material may have been used. The composition resembles Roman hydraulic concrete, yet several structures at inscription appear older than the full Roman occupation of the region. This has led some researchers to wonder whether local Celtic Iberian builders developed independent waterproofing techniques before Roman engineering became dominant. Similar debates surround ancient sites like Fishbourne Roman Palace and certain Iberian settlements, where long-lasting mortars seem technologically ahead of their accepted historical timeline. Modern concrete often begins degrading after only 50 to 100 years under severe environmental conditions. Some ancient Mediterranean hydraulic mixtures have survived over 2,000 years. That difference continues to puzzle material scientists. Inscription should have been highly vulnerable to erosion. The city sat on steep terrain exposed to Mediterranean winds and seasonal downpours. Yet large portions of its streets and terraces remained stable for centuries. Archaeologists discovered that builders layered crushed stone, gravel, clay, and compacted earth beneath pathways and foundations. This created natural drainage beneath structures, reducing hydrostatic pressure during storms. The principle resembles modern permeable sub-base engineering used beneath roads and retaining walls. Some retaining systems also appear intentionally flexible. Instead of rigid mortar-heavy construction, certain walls used tightly fitted stones with micro-gaps that absorbed stress during ground movement and thermal expansion. This technique resembles polygonal masonry seen in parts of ancient Iberia, Greece, and even certain Andean civilizations. While no direct connection exists between these cultures, the engineering logic is remarkably similar. Structures survive longer when they can move slightly instead of resisting every force rigidly. Southern France regularly experiences summer temperatures above 35 degrees C, yet excavations show many homes at inscription were designed to reduce heat naturally. Walls were unusually thick. Doorways and openings often faced directions that captured cooling sea winds while avoiding the harsh western afternoon sun. Some underground storage chambers maintained relatively stable temperatures year-round. The principles mirror passive cooling systems later perfected in Persian desert architecture, including wind towers and subterranean thermal chambers. Even without electricity, ancient builders clearly understood airflow, shade angles, thermal mass, and evaporative cooling effects. Researchers studying thermal behavior at Mediterranean archaeological sites found that thick stone walls can reduce indoor temperature swings by several degrees Celsius compared to external conditions. In a pre-industrial world, that difference could determine food preservation, comfort, and survival. One of the strangest facts about Ensarun is its economic scale. Excavations revealed enormous quantities of imported goods, including wine amphorae from Greek and Roman merchants. This indicates sustained long-distance trade across the Mediterranean, yet maintaining a large population on a dry hilltop would have required stable food supplies, water storage, and transportation systems. Some archaeologists estimate the settlement may have housed several thousand inhabitants during its peak. That would place enormous pressure on local resources. Without advanced water management, the city should have failed quickly during drought periods. Instead, it survived for centuries. The possibility that hidden cisterns, buried canals, or lost underground conduits still exist beneath the hill remains a serious archaeological question. Ground-penetrating radar surveys in parts of southern France continue revealing buried structures invisible from the surface. Some researchers believe Ensarun may still conceal major hydraulic components beneath layers of sediment and collapsed architecture. Do you think the builders of Ensarun discovered these engineering techniques on their own? Or were they inheriting knowledge from a much older lost civilization? Let me know your theory in the comments below.